we can start. Yeah, yeah. Well, we are. Yeah, we are ready. Definitely.
Cool.
All right. Hello.
Hey.
First of all, most of the time people are here for a reason, so that's why I asked them, what brings you to Latvia? What was it that got you interested, and what, after you have seen some of Latvia or Riga at least, what is it that finds do you find somewhat interesting or particular?
Okay. So I've been only in Riga actually. I arrived yesterday morning with a night train from Moscow. I'm in Moscow because my girlfriend is from Moscow.
Yeah.
And basically because my visa is changing from one period to a new period.
By the way, don't mind me, all right?
No, I don't mind, really. One visa is changing from the first period to the second period, let's say. It's a 1 year visa, but it's counted every 6 months.
Right.
And basically, these days are when I'm passing between the first 6 months and the second 6 months. And because of this, during this shift from the first 6 months to the second 6 months, I need to leave the country. Even just for 24 hours. But
really?
But I need to leave the country. So basically, I was in Moscow, and I thought, okay, I need to leave Russia for 24 hours or 48. Where will I go?
Interesting.
And flights were a little bit expensive, and also I wanted to withdraw some euros because my credit card doesn't work in Russia. So I said, okay, let's go to the closest one from Moscow. Also, trains were quite cheap.
Wow.
And so that's how actually I came up. I came out with Riga.
And afterwards you're going back?
Yeah, exactly.
Interesting.
Of course I'm enjoying. It was really something unexpected.
Any similarities or differences from Moscow? Well, other than the size.
Rather than the
size.
Yeah.
Well,
Moscow is
a
very... I cannot say I really, really like Moscow.
And who does say that they like Moscow?
Yeah. Well, I like more St. Petersburg, I have to say.
Obviously, yeah.
I'm going to St. Petersburg after I come back here. From here, I will stay 2 days in Moscow, and then I'm gonna be for 3 weeks or more in St. Petersburg. You know, there is a web platform called Workaway. I don't know if you heard about it.
Maybe.
It's similar to another one called Helpix, also Helpex. I don't know.
Is it sort of for volunteer work?
Yeah, exactly. So it's for volunteer work. It's a platform where me or you as a volunteer can find a lot of advertisement of people looking for volunteers.
Are there what?
A lot.
Really?
In Europe, there are 35,000, something like this, only in Europe. Of course, they're not all of them are active all the year. Let's say a few of them are only for summer, other are for the winter. But anyway, there is a really enormous choice, and really a lot. So you can really do anything. Of course, you Google, you search, and you see what are your attitude or the thing that you would like to do.
Yep.
You can do babysitting. You can teach languages. There is a lot of either building something or helping to renovate something.
What's the motivation for them to actually post those vacancies?
Well, for them, as far as I saw in my experiences, I mean, they give you food and accommodation in exchange.
That sounds cheap. I mean, it's not if you have
for you as a worker. Or as a
for them. I mean, if you because do you get a salary?
You don't get a salary. You work 4 hours a day.
4?
4.
All right, that's not that much.
Monday to Friday. Then on Saturday and Sundays you are free. Let's say.
Yeah.
And you're given food and accommodation. And for me, it's fair enough. I mean, I like it. It gives you the possibility to... And for example, it also depends. For example, I did it 2 times. Once I was actually building something.
Really?
And it's not that I have skills in doing this kind of stuff.
That's what I wanted to ask.
Yeah. I mean, I've been only studying all my life or working in front of a computer. But this new contact with, tools and the earth was very interesting for me.
Yeah.
I was basically building a shelter. I was in the south of Denmark in an island called Møn.
Møn?
Yeah, that's how they pronounce it.
Møn?
It's actually written M-O-N, and the O has a sort of bar.
So that's a new then.
Yeah.
Alright.
They pronounce it like this. And there is a sort of Camino de Santiago, a sort of path that people do in this island.
All right.
Camino de Santiago is somewhere in Spain. It connects to different cities of Spain.
Mm.
And they make, there is a sort of path. And so there are travelers and they need shelters.
Yeah.
And the woman needed volunteers to build a shelter, basically, to build a shelter for travelers. And I was doing this, but basically my daily tasks were like peeling woods, and those woods were going to be used by somebody else to build, the basic structure.
So they had the qualifications for building specific things, right?
It was 3 volunteers. It was me plus other 2 guys. The other 2 guys had a little bit more experience than me, so they were telling me what to do. But it's a lot. Basically, they also were Googling or going online and see, and they were every day was a new discovery: how to build, how to do this, how to do that.
Yeah.
So I was making holes on the ground,
All right.
peeling woods, and also putting some cement. At some point, we put cement inside the hole together with the woods in order to make the structure of the.
Was there any quality control? I mean, how would you be able to actually?
There was
right
from time to time a friend of the woman that was hosting us.
Yeah.
Was actually, he had some qualification, or at least he was much more expert than us, and he would come like every 2 days to see how the things were going on.
Oh, so you had some oversight then.
Yeah, and that was cool. It was very interesting experience. A little bit in the middle of nowhere, but still, you can read everything. I mean, I went there by knowing what was going on.
So basically, the vacancy is for cheap labor, but you get in exchange experiences.
Absolutely.
Yeah,
absolutely.
Traveling.
And you get traveling. And the second experience, I was simply babysitting close to Berlin.
All right.
There were 2 kids, super nice.
Yeah.
That they speak 3 languages because mother is from Finland, the father is from US, and they live in Germany. So they are 6 and 8 years old, super nice. And I was babysitting, reading books, playing with them, making yoga with them, and little things like this.
What language did you use to speak?
In English.
Didn't try to teach them Italian?
A little bit, but they were not interested. I was,
we do use Italian in Latvia as well.
Yeah.
Yeah. Most common greeting and way of saying goodbye
is ciao.
Exactly.
Yeah, but this is becoming, as far as I see, a sort of slang in many languages. Also in Moscow, they say it. Also in US.
Really?
I remember many years ago, I was in Dublin in a summer school.
Yeah.
And there was one guy from Texas, I think.
Texas.
And he was. At some point, he said ciao, and people said, you speak. Why you use Italian? Yeah. And he said, no, this is English. We said, no, this is Italian. He said, no, this is some English slang. In order to say bye, you say ciao. He said, yes, because you take it from Italian. Yeah. So funny.
So a Texan didn't know.
Yeah, he didn't know.
Yeah.
Yeah.
Do you like it?
What?
Because it's difficult for me to imagine if other countries would use my native words. It would be difficult to imagine.
Well, yes, not such a big deal. I mean.
Well, do you have any sense of
pride
or anything like that?
Absolutely.
No,
absolutely not.
Isn't Italy actually sort of divided between the north and the south? Well, culturally or...
Well, generally the south is more conservative.
Right.
Yeah, and there are like family values are very important.
Oh, that's the poor region then, right?
Yeah. And the north is more about, generally speaking, it's more about money and working. And yes, there is a sort of constant... I actually don't know how actual it is anymore, because now that everything is globalized and moving is much more easy, there is much more contamination.
For sure.
So division between north and south also, I don't know what it means anymore.
And everybody in the world now eats Nutella.
Yeah.
Yeah.
But I remember when I was little, for example, and I used to go in the north quite often because I was doing one sport that would take me to the north of Italy.
Which was it? Skiing?
No, I was a go-kart driver, you know, those little
yeah.
like machines,
Yeah.
okay, with engine, and you make competitions. So I was a go-kart driver.
And it's only in the north where you can do that?
Well, no, but most of the facilities and circuits and the best, for example...
Oh, because it requires money and investment.
Probably. Most of the industries where they would make either the chassis, how it's called, the chassis, or the engines, and also the best technicians, you know, people that could work on the engine, they were from the north. So they were much more qualified. And so I used to go there because the people that were following me were from there. And I remember the first time I went when I was around 12, 13, seriously, for me it was a complete shock.
Why?
I mean, now probably, maybe this is something that doesn't exist anymore, but going when you are 12 in the north for the first time was shocking because... At least, I was mostly in villages where people maybe are more extremists, I don't know. But I remember that, for example, there is a name to call people from the south. I don't know if people...
A derogatory term? Or?
Yeah.
No, what is it?
But, you know, it can sound also... It depends on the way you say.
So what is it?
So people from the north used to call people from the south terrone. Terrone, which is something...
So it sounds like with earth. Something
exactly, because earth is terra.
Yeah.
So terrone, I don't know actually the origin of this. It must
Earthlings? Like earthlings?
No, earthling is...
People of the earth?
No. Terrone actually doesn't have a meaning.
All right.
But it's like probably you are related to the working with the earth. I don't know.
All right.
Like maybe person from the countryside.
I get it.
But yeah, they mean it generally...
How do you call in Italian a farmer?
A farmer, contadino.
Contadino. Nothing with terra.
No.
All right.
Yeah, it was derogatory, and generally it has a bad meaning. Yeah, and I remember.
I already forgot. Terrone. Terrone.
And let's say I would be there living without my family for 2 weeks, let's say, or 1 week, sometimes 1 month in the summer, and I was called by anybody, any single person would refer to me calling me terrone.
Meaning in a bad way or just...
Well...
Oh, terrone.
Yeah, terrone. Like to say, here's the terrone.
Yeah.
Let's say probably
I get
the way they approach people from the south is like a person from the north of Europe would approach Italians in general. You know, seeing them...
How do they approach?
Like seeing them like not serious, like for example now you just did tan-taran, you know, exactly this way, you know. But, so they would probably.
But come on, this is the Italian stereotype.
Well, yeah, it is. So, but that's what they would say that's proper from the south of Italy and doesn't belong to them. You know what I mean?
Yeah.
So that's the approach I would say.
But it doesn't sound that bad.
Well,
it's just sort of nagging each other.
It depends because, for example, I don't know how strong it is anymore, but
it's not like in Catalonia, right?
10 years ago, there was a politician party called Lega Nord. That it was, you know, in the program, the basic program was to separate North and South. Then it didn't happen.
20 years ago?
Yeah.
No, not that.
Also 10 years ago. No, I mean, it started probably 20 years ago.
Yeah.
But let's say the peak was actually still now. But probably the peak of popularity was for 10 years ago.
Yeah.
And the goal of them was to separate North and South because they say, you know, that the North is working. But I think this happens in every country. The North is working and the South is living on the shoulder of the North.
Mm.
And the south of Italy slows down the north part of Italy, and because of the south, the north cannot be as rich as it could be.
Yeah, for sure. That's common. That's common everywhere. Yeah.
So I don't even remember how we got talking about this.
Well, you are Italian.
Yeah.
That's how.
Yeah.
You are an Italian coming from Moscow, just because you need some at least 24 hours
Yeah, it's funny. actually.
exile,
Exactly.
and now you're
exactly.
here in Riga.
Exactly.
So what did you do? What were the things you did in Riga?
In Riga? Well, yesterday there was a sort of snowstorm, if you remember.
Mm-hmm.
So I arrived actually at 8:30 in the morning from the night train. I was very sleepy, and I just went inside a cafe for many hours actually, and I started working on the computer. So I spent at the cafe a lot of hours. So I didn't really walk a lot around. I just was walking around the neighborhood where you live. And today I basically I was walking in the old town, and then again I was googling some nice cafe, and I was searching for a cafe, but I didn't like all those where that I found on Google. So I went first to one cafe that I found on Google. I got in, but I didn't like it. Then I went to another one, then another one. And at the end, I ended up in the same cafe where I was yesterday, which is basically just here, just almost in front of your door. And I was there in the afternoon. So let's say half of the morning I was walking, and second half and taking pictures. Second half I was in a cafe working on the computer a bit.
Yeah. Sounds fine.
Yeah, and tomorrow I'm actually coming back. So I'm aware I didn't see a lot of Riga. But who knows, maybe this is the first of many times. A lot of people I spoke with, I managed to speak with 3 Latvian today in the cafe.
Real Latvian?
Yeah. And they all told me, but you should come in the summer. In winter, nothing happens.
Yeah, that's usually the case for sure.
So who knows, maybe I'm going to come back in summer.
Come on. How long have you been in Moscow?
In Moscow, a couple of months.
And before that?
Before that, I was in Italy.
Oh, all right. So you haven't forgot how warm Italy is, probably.
No. Actually, yeah. Now it's around 14 degrees, I think. Depends on where, but...
Because that's what I would imagine. I mean, and for an Italian to come in the cold months to Northern Europe...
Yeah.
It's not really common, I would
It's
imagine.
not. Actually, the coldest temperature that I experienced where I was more in the continental Russia 10 days ago. I don't know, maybe 1,000 kilometers more in the center.
Yeah.
In a city called Perm. And I went to Perm because the makers of one of the instruments that I play, that I will show you later, are there in Perm.
All right.
And because I'm going to start a collaboration with them, and I said, well, I'm in Russia, I have a free time, why not going to Perm? So I went to Perm, and again I went with night train. Night train is actually a daily train.
All right.
And there was -20, -18, actually -18, but it was because it was windy and it was feeling like -28 actually.
Sure.
And for me, I have to say, as an Italian, probably I was never below -5.
There you go.
So -18 was new, and I was observing the physical reactions of my body. For example, I noticed that I had a lot of pain. The most noticeable thing was having a lot of pain in the tip of my fingers. Until -10, you can handle it, but after -10, it was just unbearable. After 15-20 minutes...
You didn't have any gloves?
I had gloves, but still. Funny, because my girlfriend didn't have this problem, maybe because she's from Russia, I have no idea. But my body probably is not used to this.
For sure.
And more than 20 minutes walking at -18, let's say, it was physically pain in the tip of my fingers.
Yeah.
So I just had to get inside either a cafe or simply a building,
drink some vodka.
or a mall. No, simply a mall. I would be in a mall for 10 minutes in order to, make the pain away.
Did you drink any vodka in Russia, or do you plan to?
Well, they offer me.
Italians are wine drinkers, right?
Yeah,
most of the time.
But Italian in general, we don't drink a lot. At least really? Me, I don't drink a lot in general.
So what's the drug of choice?
Well, as far as I know, I think we are one of the population that drink the least. But when we drink, it's mostly wine or beer. Yeah.
Really?
Yeah. And people offer me vodka. Last time was in the train. Actually, there was my train mate.
Yeah.
He was offering me vodka all the time, and of course, as soon as I finished the vodka that he would put me in the glass.
Yeah.
He would put me new one. And because he didn't accept me saying no, he would complain and start swearing at me.
For real?
Well, I mean, in a nice way, but he would say, why no, like this. So at the end, I didn't finish the last glass. I left a little bit, so he couldn't add more. But this way I drank three times vodka in the train. And also when I go to the... during special events, let's say for the birthday of the dedushka of my girlfriend, for example, there was vodka all the time. They were offering me vodka all the time. Actually, everybody got super drunk, I have to say, out of vodka.
So it's still something that happens commonly.
Yeah, I would say yes.
People get
drunk
on vodka.
The father of my girlfriend also, for example, they say, you didn't digest, drink vodka. Or you're still not hungry, so first drink vodka and then eat. It's like a sort of everyday...
But does he look healthy?
Yeah.
Does he look like a person who knows what's healthy or not? Yeah. Well, anyway, I mean, I guess if you don't feel pressured, then it's all good.
Yeah, it's okay.
Then it's all good.
Yeah.
All right. You had some questions on your own, right?
For you...
Again, well...
Yeah, well, while we were talking before, I had a lot of questions. One thing that I was really... I like when I travel, couch surfing, all this stuff, of course, like everybody, because it's not only about traveling, it's about being inspired by people, having new perspective. And because we didn't talk about many things, but in May, I quit my job.
So what was your job?
I'm an astrophysicist.
Wait a second. Astrophysicist would be a profession, right? But
yeah.
Is it really basically a job description?
Yeah.
Astrophysicist?
I was a researcher at university, basically.
All right.
So basically doing what is called basic research.
So it's an academic position, sort of.
Academic position.
All right.
I was working at university.
Why astrophysics? And what is astrophysics? Please explain. I would imagine astrophysics is something that was not present before the Second World War. Was it? Well, I imagine astrology and I imagine physics. Yeah. And maybe after Einstein, they just combined or what?
Well, okay, maybe...
Is astrophysics the inspiration for the Big Bang Theory, for the TV series?
So let's say there is physics and there is astronomy.
All right. Astronomy, all right.
I would say that now, of course, now you can... Basically, an astrophysicist is a physicist. Is somebody that was studying physics at university.
All right.
And then taking the specialization in astrophysics. While an astronomer, now there are universities where you can study astronomy. Mm-hmm. So an astronomer is somebody that graduates in astronomy. An astrophysicist is a physicist with a specialization in astrophysics, in astronomy. But as a matter of fact, it's really the same thing. It's the same thing. Maybe astrophysicists study a little bit more physics than astronomers, but it's really the same. They are synonymous nowadays.
So what are the problems that you would be researching?
Yeah.
Because I would imagine, because here's the thing. I don't know much about it, but if, let's say, people talk about the Big Bang Theory.
For example, of course.
Yeah, it doesn't make more sense for me than just the creation theory, to be honest. Hey, look, something wasn't there and then something popped up.
Well,
all right.
That's the thing, because...
Right? Because as far as I understand, the Big Bang Theory would be just explainable from the known laws of physics, right? Mm-hmm. As far as I understand, that's why it's considered a valid theory. Mm-hmm. But you wouldn't be able to tell. No, it's definitely how it happened, right?
Well, so
take your time.
Yeah. So basically, in physics, you have observations.
Right.
You observe something. Then you try to explain what you observe through a theory.
All right.
And a good theory is something that has, let's say, at least a couple of requirements. One is that is able to explain all the observations.
Oh, wait a second. Wasn't the first instance for explaining something a hypothesis, and then afterwards you make a theory out of it? If you really make the observation, what's it called? Not controllable, but you can do it again and again. And
okay, so let's say you make an observation, then you make hypothesis on what could be the mechanism behind what you observe.
Then you test it.
And of course, the hypothesis come from a framework, which is the theory. So if the theory...
you mean like an assumption, sort of?
Yeah.
All right.
So if the theory explains everything that you observe in a coherent way,
All right.
without requiring too much ad hoc,
All right.
add-on, let's
Yeah.
say. So a good theory, A, explains all the observations that you do, and B, I would say, and of course you can make it's something that can go through a falsification process. So it should allow you to make experiments to say this is true or this is not true.
All right.
And secondly, a good theory is a theory that make predictions about something that you still didn't observe, but that following the theory should be true. So let's say you say, okay, I make this theory, so I make this observation.
All right.
I try to explain this observation and I come up with a theory. And then the theory also says, look, if everything that I'm saying is true, then not only I can explain you everything that you observe, but I will tell you that this other thing should be true or should happen, something you still didn't observe.
But it's something you would need to imagine that should also be the case. But I would imagine that not for every theory there would be something auxiliary to be added. It would be difficult.
Well, for example, in the case of general relativity, Einstein said, okay, the gravity works this way, and for example, the reason why there is gravity is because something that is massive curves the space-time, which was a completely new and crazy concept for that time, and even for now, actually, thinking that something that has a mass, even my body, is curving at the present moment the space-time. Is curving the space-time. And because the space-time is curved, objects that are near a curved space-time, for example, the moon that is close to Earth, makes a curved trajectory and orbits around Earth because the space is curved by the presence of Earth.
But what's the dimension of space-time? How do you actually establish the dimension of space-time?
Dimension, you mean how many, the real dimension? So it's three physical dimensions,
All right.
three spatial dimensions,
All right.
length, let's say,
Yeah.
plus the time.
So how do you use it as a dimension then? Time. I mean, all right, time passes
Yeah, well,
by,
because time multiplied by the speed of light, it's super complicated to explain, but time multiplied by the speed, time times a velocity, it's a space. So basically, the third dimension is c, which is the speed of light, times t.
Well, is that the equation that explains the dimension, or that defines the dimension?
I'm not sure understanding what you mean.
Well, I mean, how do you, let's say, a dimension in just a spatial sense would be observable, right? Right. So how do you capture the dimension of time?
Well, this is something. This is one of the things that probably we still have to understand. I mean, living in a three-dimensional space, it's basically super complicated, if not impossible, to imagine a fourth dimension. Like if we were two-dimensional beings, it would be impossible to imagine a three-dimensional world.
All right.
So imagine it or trying to figure out how the four-dimensional space-time is structured or how it looks like, I think it's beyond the
space-time
capabilities of our mind to imagine how it looks.
Is space-time supposed to be something that can be measured in a way? Or is it just a concept that can be useful for using it for theories, explanations?
Well, I mean,
because in a sense, if you take spatial dimensions, right?
So you want to say space, you can measure it, right?
Yeah, and you can see the correlations directly affecting each other. If you have an object, right, and you sort of try to take one dimension away, you would affect the other dimensions almost always. Well, sort of. So that's what I mean.
Well, basically, the space-time, the space-time is related to let's say, the additional information that you have is that this object not only has its size, but also that at a certain time it's here and another time it's here.
Yeah.
So this is the additional information that you're adding.
It's just different location at a different time, isn't it?
Yeah.
All right. So where was the time-space dimension or space-time dimension?
So the information that comes from this fourth dimension, let's say, is related to the position of the change in the position of the object in time. Then if you ask me more details, and if I cannot say more, it's more for my personal incapability of explaining it, and not because of something missing in the theory.
What I mean is space-time something static? I mean, because time is fluent, right? In the sense that time just passes by. We know because everything just grows and dies, grows and dies. All right. But other than that, we can just capture time in a certain moment, and that's about it. So at this moment, the mouse is here. Next second, it's over there. So was it related to the space-time in any shape or form? Now. The changing of locations. The simple fact it changed locations, or
yes. Or what?
Or the fact that time passed during those changes.
The fact that the time passed during the changing, yes. So let's say you have let's say the position of an object is not only given by, you can take a set of coordinates, let's say that start from that corner, and you can measure the distance, the position of this of the mouse.
All right.
Let's say the mouse is 2 meters along the x direction.
Okay.
1 meter along the y direction and 1 meter along the z direction.
Okay.
This is in the normal coordinates, and then you say at time 8:53. So you have an additional, it's x, y, z, and t.
All right, but if that position would be to change, then only because some force would move it, right? But if not if not, time would still go on. Time would change.
Yeah.
So space-time would mean that something changes its location while time passes?
So, like I said, you have those three defined positions at time 8:54.
All right.
And then at time 8:55, it can be either in the same positions for another time. So
8:55, yeah.
Yeah, or in another position. That's it.
And it doesn't matter if it changed position, doesn't it matter what caused it to change the position?
Yeah, of course it matters, but it depends on the problem that you are studying, yeah.
All right, so you were saying about the space-time then.
I was making an example of what a theory does.
All right.
And in 1916, one of the consequences of this general relativity was that, space-time is curved. If space-time, and that's why we have gravity. If space-time is curved, then we should see also the light. Let's say you have the sun, and there is a star in the background of the sun.
All right.
And we are here.
Yeah.
Let's say there is the light of this star. If the light of this star passes near the sun, light itself should not go straight, but should make a curved trajectory and be bended by the presence of the sun. People said, what the hell? What is this? I mean, life. The trajectory of light to be curved, this is crazy. But this was a consequence, a prediction of relativity.
All right.
And 3 years after, 1919, this observation was actually made, and it was observed the light of a star that was behind the sun curved by the presence of the sun. So this was a prediction of general relativity. It was the first confirmation of the theory, for example.
So do I understand correctly that it's meant to be as if you would have a laser pointing at, let's say, the sun?
Yeah.
So the laser would just shine around it?
Well,
Because that wouldn't be possible, right?
It will make a curve.
What?
I mean, in principle, also if I have a laser here passing next to the mouse will curve the trajectory of the laser.
Well, it definitely will.
I mean, it depends on the mass, of course.
But it would have to be reflective in order for the star.
No. I mean,
laser to still go.
Anything that has a mass curves the space. Let's say.
I would imagine it's just an obstacle for the light to actually pass.
No. It's not. Sorry, the light didn't pass through the sun. It passes next to the sun. So of course, the more you're close to the sun, the more the curvature is big. So the effect is more visible. Let's say.
All right.
And this phenomenon was actually possible it was easier to observe it during a sun eclipse because the light of the star behind was not let's say there was not the light of the sun that was much brighter, so it was easier to observe the star that was behind the sun.
All right.
And basically the star appeared like it was in another position because its light was curved. So let's say you are here on Earth, and if the light goes straight, you see that the star is here.
All right.
But if the light is bended and you're here, it looks like the star is here actually.
All right, I get it.
Although its apparent position is here, although the real star is here.
Yeah.
So during that first observation, then it was the same kind of experiment was made in the last 100 years, many times. The star actually appeared like its position was different from the real one.
So,
and this was the first confirmation of relativity, but then we had just so many. The last one was 1 year ago.
So does that mean that the people on Earth are observing this place and they definitely know that here nothing is actually there present?
Mm-hmm. So
but
basically,
from there they see that something shines here, right? And then how do they figure out that it's actually coming from there?
Well, because you know the exact position of the star. You know it because, for example, you know where the star is in general, no? It's like you know the night sky, and you know that extremely precisely, you know where a certain star is at a certain moment of the night. You know the star is there. But then only that day you see that star is there all of a sudden.
Yeah.
For example, this I mean, of course now I'm exaggerating, but this is what happened.
So there's no real option that they actually are looking here and seeing actually something that's actually here?
No, it was that star. I mean, it was that star appeared like it was somewhere else, as a consequence of the fact that the light of the star was bended by the presence of the sun.
And they for sure knew that nothing could be here.
Yeah, of course. I mean, they knew what.
How did they do?
They knew what they were observing. People know the night sky, no?
It sounds weird, to be honest. It sounds weird.
Well, but
because in a sense, I would imagine, let's say, for instance, if I have a laser pointing at the...
No, not at. I mean, gravity is a field, so it doesn't.
Yeah, but the point you were making is
it's a distant action.
Yeah. Light is somehow shining here, and because of this, and somehow gets somewhere around there, or
no. So
like that.
Let's say I have the mouse.
Yeah.
And I with the laser, I make the laser pass. Let's say here. So. Okay.
Oh, not even touching the.
No, not even touching. Of course, not touching. It's a field, so it's a distance action. Let's say in principle, let's say you have a laser fixed at that position of and you know that the laser is always, it's an.
Yeah, all right.
It reflects on a very precise spot on the wall.
All right.
At some point, you come with the mouse or something possibly heavier.
All right.
And at some point, when the mouse, for example, is here, you will see that little spot will be not there, but 10 centimeters.
That doesn't sound that could be true.
But this is what happens, and we observe this all the time.
But could we actually test it with a mouse?
With the mouse, not because it's too little the effect. But we see.
Oh, so you need a certain mass?
Yeah, of course. The more the mass is big, the more the effect is evident. That's why we need stars. Gravity in general is something that.
So in a sense, you wouldn't be able to actually make your model. You need observational evidence.
Yeah. I mean, you make observation through.
How would you be able to actually make a model for that in an experimental way that you can actually use a light source? You can have an object. Just proportionately smaller as a star.
Well, no. As far as I know, these kind of experiments on Earth were not done, but simply because the effects are too small. But you have the sky, which is full of.
Technically, it should be possible, right? Because you just take the mass.
Technically, is what happens.
Make it smaller.
But the effects are super small. Technically, also the mouse is attracting me, and I'm attracting the mouse. But you don't see me falling inside the mouse now because the effect is small. It's proportional to the mass, actually.
Also, everything is based on observational evidence, then.
Yeah.
Oh, that's a little bit tricky, isn't it?
And now I tell you another fact of general relativity.
All right.
It's not only that the space is curved, but it's also that the time is stretched by the presence of something that is massive. So, for example, the core of Earth is, let's say the central part of Earth, because the center of the planet is more dense, so it's proportionally more heavy, while the surface of Earth is farther from the more massive part of Earth.
All right.
Basically, it happens that the time passes slower. Let me think. The time passes slower at the core than at the surface.
How would you be able to actually?
Now I go back.
Isn't
actually
time a comparative
another
measure?
measurable effect of gravity? Another effect of gravity is the fact that in regions where gravity is higher, the time is slower, and for this reason, the core of our planet is 2.5 years younger than the surface of Earth.
Yeah, but my question would be, isn't time a comparative measure in a sense that you only can measure time by having at least two different points in time, in a sense that, all right, how could you tell that a person gets older? Mm-hmm. You just compare it to when he was younger. It looks changed and stuff like that, right? So how would you be able to tell, time actually passes, and it passes not so quickly here and a little bit faster there? So
one way to see this is through the GPS satellites. GPS satellites help us, give us the position of an object on Earth, right? Okay. And actually, the position is measured by a time measurement. So what you do is you have a satellite. It sends electromagnetic signal on Earth.
All right.
On, let's say, some base. And then the signal goes back.
All right.
Because you know the speed of light, which is a constant, by knowing the time it takes to from the satellite to Earth and from Earth back.
All right.
From a measurement of time, you have a measurement of distance, actually, because you know that it takes, let's say, 10 seconds.
Oh, so it's a comparative then.
The signal to go and come back takes 10 seconds, let's say.
Yeah.
And you know that the speed of light is a certain speed, which is a constant. And so from the speed of light, you know actually the distance between the satellite and the point of Earth.
But is the communication light, or is it some form of frequency?
I said, electromagnetic wave, which goes with the speed of light.
Okay.
The speed.
It's like electromagnetic waves to travel with the speed of light?
Light is an electromagnetic wave.
So basically, they are,
light is an
so that means light transfers information? Or is a conductor to any data?
So light, yes, of course. I mean, it's a wave. So So light is an electromagnetic wave. So also a radio, for example, when a radio signal is actually the same thing as saying light. Yeah. What we call light is an electromagnetic wave that has a certain energy, which is what we call the visible band, that has an energy between 0.5 and 3.5 electron volts, let's say. What we call the radio wave, it's something that has an energy that is 1 million of this number that I just said. Something we call X-ray is just the same as a radio wave signal, just million of times more energetic. But it's still the same thing. So when we say radio, or when we say microwave that we use in the kitchen, or when we say light, or when we say X-rays, when we say infrared, we are talking about the same thing. Just different energies of the same thing, which is electromagnetic wave.
Oh, all right.
Yeah.
Well, it's difficult. It would be difficult to grasp what would be, how to actually sort of understand an electromagnetic wave as it is, because in a sense you wouldn't be able to see it as a wave and then more waves or anything like that, right? It's just that you know it exists, right? In a sense that you know how to use it.
Well, for example, if you have an antenna is basically a detector of an electromagnetic wave.
Yeah.
So that's how we detect signal, for example, from the radio waves that we produce.
Because if you say that general relativity was some form of almost like revolutionary thinking, wasn't the first revolutionary thinking to actually try to explain to somebody, well, I think, this thing you don't really see,
of course,
actually transfers some form of energy, right?
Of course.
Energy.
Of course. Yeah.
And so who was that guy?
The first people talking about electromagnetic waves 100 years before, there were a few people. I don't know who was the first time they came out with it, but the people working with it were Maxwell for sure, Faraday, who else? I don't know.
All right.
Yeah. Anyway, about the GPS satellites, I was telling you, we measure distances through a measurement of time, like I just said. Because in the GPS you have atomic clocks that are super precise until nanoseconds or even more. So the precision. So an atomic clock is able to measure the time with a precision that is 1 billionth of a second or even more. Okay, so this is the precision that we have.
Compared to another...
So let's say you can say...
Atomic clock?
Atomic clock can measure time with a precision of 1 billionth of a second.
Of another atomic clock. Because look, an atomic clock would just count numbers, right? Is it true? So it just counts number as a general clock.
Yes.
But the what would be the case? Not the frequency, but still the proportionate movement of the counting is so identical to a nanosecond, right?
Yeah. Let's say honestly, I don't know how an atomic clock works.
Yeah.
But let's say the smallest step, the smallest increase, let's say, is of the order of nanoseconds. Okay. Now, the effect that I was telling you is, let's say that you have an atomic clock. No, let's say we have an atomic clock on the satellites, and we have another atomic clock on Earth. If the two atomic clocks measure the same time, let's say they are synchronized now in this moment. Okay. After 1 day, there is a shift between the two of them of, let me think, something like 50 microseconds. So a microsecond is 1,000 of times more than a nanosecond. So 40 microsecond is, let's say, 40,000 times more than 1 nanosecond. So basically, after 1 day, the clocks on Earth and the clocks on the satellites are not anymore synchronized, but there is a shift between the two of them of 40 microseconds.
All right.
Because of this shift of 40 microseconds, the distances that they measure are not anymore correct, because we're not talking anymore about the same time. It's like I tell you, this car, it took it 3 minutes to go from here to here, and you tell me no, it was 4 minutes, because your clock goes differently with a different speed. And so we don't agree anymore with the for example, with how many meters the car did, because for you it was 200 meters, for me it was 150 meters. Okay. Because of this shift in time, the GPS would give us an error in the position of 10 kilometers per day.
All right.
So after 1 month, we will have an error of 300 kilometers.
Mm-hmm.
And because of this, so basically this is a situation in which the effect of general relativity are in our daily life. The clocks in the satellites had to be engineered such as the time goes a little bit faster, because they had to correct this effect, because if this effect was not taken into account, or our GPS would give 100 or 1,000 of kilometers of error in the position.
Oh, wait a second. So you are saying that basically you could take two identical atomic clocks, put them on Earth, and they would be synchronized, everything is in
but if
sync.
you put one of them
but if you transfer it a little bit above, after a while they
are
shift.
desynchronized. Absolutely. And
Oh,
that's why the clocks on the GPS are actually wrong.
So the conclusion is that time passes slower. Maybe it's just because a physical effect on the mechanics is causing it to count a little bit slower.
But it's exactly the amount of change that you expect from general relativity. Actually, there are two effects.
So you expect it from general relativity?
From general relativity, you know exactly how much the time should be stretched.
So does general relativity say that the distance between the objects or the height, let's say, do you need an atmosphere?
No. It's the distance. It's not related to atmosphere, the distance.
So if you would take those both synchronized clocks out into space and then take them apart at least with a diameter of, I don't know, Earth.
No.
Would they?
It's actually it is influenced not by the distance between each other.
All right.
But by the
mass of some object.
By the distance between the clock and some massive object.
So
basically, the atomic clock on Earth is closer to Earth than the one in space, and because it's closer to Earth, the action of gravity on that clock on Earth is stronger, and so time in that clock is slower.
Slower or faster?
Passes slower.
Slower?
Yeah.
So that one in space is faster?
Yeah.
Oh, all right. So if you take both of them out of the Earth's orbit, put them near Mars, for instance, it wouldn't necessarily be the same slowness, fastness as on Earth, right? It would be some sort of another form of...
it depends on the mass or where it is. For example, if you imagine to be next to a black hole, which is a very massive object.
But a black hole is also something that can be observed and theorized about, right? But how would you actually imagine it existing in 3D space?
Okay, black hole.
As far as I understand, there's no real explanation what's in it.
Okay, so black hole, first of all, they came as another consequence of general relativity. And people said, not Einstein, but people said after him, okay, if this is true and if a mass curves the space-time, then a mass that is big enough should curve the space-time in a way that it will be completely curved, and light itself cannot go out from this from the star because the trajectory of the light goes back. So basically, light is emitted and goes back.
It's just too big.
It's just so massive that the space around it doesn't allow any more straight trajectory. So, for example, also light goes like this.
All right, but space is infinite, right? So how would you find an object that could be so big?
No. Sorry, is this? Imagine space. Imagine.
Oh, you mean the mass of the object being
space
so big, right?
Like a net, or like imagine a two-dimensional piece of paper.
All right.
Imagine a two-dimensional piece of paper, a sheet of paper that is flat.
All right.
And then imagine to have a little ball, and you kick the little ball.
All right.
And the little ball goes straight.
All right.
Okay. Or imagine a very big, or imagine a towel. It's easier. A big towel for the kitchen, for example.
Yep.
And the little ball goes straight. Then imagine to put a bowling ball in the center of the towel.
Mm-hmm.
It will curve the towel. At this point, you
mean press.
It will press the towel.
Press into it.
It will press the towel, and the towel will expand in the third dimension, in Z. Before it was a two-dimensional object, then it becomes a three-dimensional object, the towel.
All right.
At this point, if you have the little ball and you kick it, it will not go straight anymore, but it will make a curved trajectory. So this is a two-dimensional example. Sorry, this is a three-dimensional example of what actually happens in 4 dimensions.
It's only, but does it matter that the bowling ball would be it would be prone to gravity in that case, because in space it wouldn't curve the towel, right? It would just float, right?
So now I'm saying that because there is this bowling ball, the surface where the little ball leaves is curved. So the same thing happens. The space-time, which is imagine when I say space, I don't mean the amount of space that is in, for example, in one room. I mean the structure where we live.
All right.
So the structure where the universe lives is curved itself, and because of this,
is it curved as in a sense that some force as gravity is pulling it? Or modeling it?
Gravity is the consequence of the fact that a mass curves the space. So basically, gravity curves the space, and the geometry of space is affecting the movement of objects.
So when it comes to the bowling ball on the towel, it's more or less the same as it's not the same as the towel and bowling ball being out in space, right? It's not the same.
You're right that if it was out of space, this was only an example to make you see that.
Well, there's the third dimension when the object is somehow impacting the two-dimensional object, right?
I didn't get you.
Well, I understand that the example was to see that once the massive object is impacting another object, there's this third dimension just because of the force.
No, let's say that it's not impacting. Once the massive object, let's say you imagine the two-dimensional towel as the reality where you live.
All right. Sounds easy.
And at some point, you add something massive. Okay, in this particular example, the curvature is due to the fact that there is gravity because we are next to Earth. Yeah.
All right.
But this effect I'm talking about is actually the explanation of gravity itself. So even if you are in open space, it happens, and this is what actually happens.
And you would be actually able to observe that by looking in outer space?
Yes.
Only by looking out of space.
For example, among the many, for example, one of the observation was the curvature of light that I told you before.
All right.
This was a observation of the curvature of space, actually, because the space around the sun was curved. That's why light was curved itself, and that's why the star appeared like it was somewhere else. Another more recent example is what we call gravitational lensing. So we see, and this is another fact predicted by general relativity. When there is a massive object, or not really star, you see this more with cluster of stars, or even more with cluster of galaxies, something very massive. The light of whatever is behind it appear like makes this kind of shape. It's completely curved like this
around the massive object.
Yeah, so you see a massive object here,
but
and then all around the massive object you see things like this.
But the object
like little rings or even complete rings.
But the object doesn't need to be solid in one piece, right?
No, actually, it actually is not.
All right.
It's a cluster of galaxies. So if you Google later the Abel cluster of galaxy, you will see, just Google it and go on Google Images. You will see a lot of pictures where there is something massive in the center and then lights making this curved, funny trajectories. Very big, actually, even like this. And those are, for example, you see galaxies that are supposed to be like circles, but actually they look like arcs.
All right. Because they need to get around.
If you ask me why, I honestly don't know why it has particularly that shape, but I know that exactly that shape was predicted by general relativity.
Also, is general relativity some form of set of formulas? Or is it just basically, well, if an object is it will be just round?
Well, everything, like they say, language of physics or language of nature is mathematics. So yes, it's a huge theory with a lot of formulas. Yes. But then because you have the good about formulas, the good thing about something that is quantitative is that's why it's easy to falsify a theory in physics, because as long as you have formulas, you can tell exactly what is supposed to happen. And if what is supposed to happen from the formulas doesn't come out, means that the theory was wrong.
In total or just in one part?
Yeah, just in one part. Usually what can happen is two things. Either you find a new theory that replaces completely the first theory, but this, I don't know if this can happen anymore in recent times. Rather, what happens generally is that the old theory is a particular case of something that is more general. So, for example, the Newton theory before, that was explaining, for example, gravity before relativity, is just a particular case of relativity that holds in a more specific condition, where general relativity is more general. So a new theory, when we will come out with a new theory, for sure we'll come out with a new theory. This doesn't imply that general relativity was wrong, just that it was a particular case of something more general. So usually a new theory embrace the old one and generalize it in more larger, broader situations. And
have there been any upsets for astrophysicists in the last 50 years that they concluded, we had this all wrong, or some big theory, or some wrong, or something false?
Yeah.
So what was an example? Do you know anything?
As far for relativity, actually no, because until now relativity was so stubborn that it was proved correct for hundreds of years. The last confirmation of relativity happened 2.5 years ago.
Do I understand correctly that the possible proof that the general relativity theory would be incorrect would be to actually say, all right, I will, let's say, look at the massive galaxies and I will see the shape of the light
Yeah.
in one way, and if I see it in that one way, then I have proven my point.
Let's say that.
But if the theory is correct, then the light should be somewhere around like this.
Yeah. So
Alright.
let's say that from the
It's a little bit weird because it seems to me that you need to make predictions and then just watch out you, because the best way would be, all right, if the theory would be correct, we will make a model.
Yeah, but
and then we will just on a really real small scale just show it.
But you cannot do this in gravity because gravity
gravity
holds with big masses.
So gravity is the consequence of the general relativity, in a sense.
No, I mean you cannot do this with gravity because the effect of gravity are more evident. The more something is massive, the more the effect are relevant. So with smaller objects, you cannot make experiments where the effects would be relevant.
So if you could make a box where you don't have the gravity somehow affecting it inside, then it would be legit, right? But I guess it's not physically possible.
No, because gravity in our case comes from by the fact that we are on Earth, so you cannot remove the Earth as long as we know gravity. But maybe this will be possible when we understand gravity more. For sure, for example, the clear evidence that gravity is not complete is that...
What do you mean gravity is not complete?
That the theory of gravity is not... the theory of general relativity is not complete, is the fact that there is no communication point between quantum physics and gravity. This is something that everybody knows. We know that at some point we cannot explain gravity with quantum physics.
I'm not sure what quantum physics does. So astrophysics looks at the stars, and quantum physics?
Physics study the macro world, the world of something that is very small. And for example...
And why would they be interested in explaining gravity? If gravity is related to the mass of an object, right?
Yes, but for example, like I said before, the theory, for example, of general relativity can be under certain conditions. For example, in the case of small mass, can become the theory of Newton. So general theory of Newton is an approximation under certain conditions of theory of general relativity. So
it's a subset of the theory then, in a sense.
Yeah, of
it's
course.
A part of it.
Yeah.
All right, but when Newton formulated it, he meant it to be that's the all.
Well, that was the state. That was
right?
the state of the art for its time. So basically, you cannot explain general relativity through quantum mechanics, and the two theory do not meet. There are this is more for.
Does it mean that some of them, parts of either one of them are wrong?
Yeah.
But nobody knows which, or what?
Nobody knows which. Yes, this is if you ask me what is the biggest challenge of physics in 2000, now in the 21st century, is the incompatibility between general relativity and quantum physics, and people know that because
what is then the assumptions of quantum physics then? What's the difference then?
Well, this is getting really complicated for me.
Really?
Yeah. I mean, talking about quantum physics is really complicated for me now. But basically, quantum physics describes how the world of atoms or particles behaves. For example...
also by observation? Or by theoretical modeling?
By observation, yeah. Of course. For example,
how do you observe atoms?
Well, for example, there are a lot of experiments made, more or less, again, 100 years ago, that were completely, it was impossible to explain them with the classic physics, no? For example, the fact that a particle can behave like a wave, or that a wave can behave like a particle.
So
And there were, for example, experiments where two particles passing in a...
the double slit.
Yeah,
All right.
exactly.
Yeah.
In the double slit, you see, let's say you have, I actually don't know what slit means, but I
Those
guess.
small,
yeah, exactly, that one. So then you see the figure that is after the slit, let's say, and you don't see, you imagine to have a gun with particles, and the particle can either hit the wall or pass through the,
the slit,
yeah. So supposedly you should see one spot on the left and one spot on the right.
All right.
No, and if you shoot simultaneously, you should see one spot on the left and one spot on the right. And actually, what happens is that if you shoot only with the left one, you see one spot on the left. If you shoot only with the right one, you see one spot on the right.
All right.
If you shoot with both simultaneously, you see spot on the left, spot on the right, and a lot of spots in between.
All right.
Which is exactly what happens when light passes through to this world again, which is the interference patterns. No, you see regions that are more dark and regions that are more light, more and less bright, and this is a consequence of the interference between the waves. When two waves are
because of the object.
When two waves are
colliding.
Not colliding. How do you say this?
When
they had the same phase.
All right.
The intensity sums up.
All right.
While when they are in counter phase, they cancel each other. Right.
All right.
So, for example, if you have a wave on a lake, two waves on the lake, they interfere with each other. If they have the same phase, the resultant wave would be just the sum of the two of them. While if they are like this, the resultant wave will be zero.
Yep.
And the interference pattern is typical of waves.
All
so
right.
when you have two waves, for example, of light, you would see figures you will see regions that are more intense, regions that are less intense, because of this behavior. And the surprising thing was that you could see this also when you were shooting not light but particle. Let's say you had two electrons.
And there's no way that particles could behave like a wave by themselves?
That's the thing. Particles behave like waves.
And why is that surprising? Because if that's an observation, all right, so be it, isn't it?
Yeah. But then people had to accept that matter can behave like a particle. Like a wave. You had to accept it was a very big change of paradigm to imagine that this table is producing waves now. It's actually a collection of waves.
But in what sense would that be relevant to say that a physical hard object is some form related to waves, Does it really matter?
Well, because
we can see it's hard matter.
Exactly. And we could also see that a particle is hard matter, but then we had to accept the fact that it was under certain conditions it was behaving like a wave.
All right. On a bigger scale, though, we wouldn't be able to shoot two desks through big slits and then see that the desks are not just through the slits,
just because
but they are
just because
scattered,
the effect will be less evident because exactly it's a massive object, so this effect will be much less evident.
Shouldn't it be much more evident because it's a bigger object?
No, because that's how.
Interesting. So a smaller object would get bigger differences?
Yeah. Now I cannot tell you why. I should think about it. But yes, it depends. It depends on that. Yes. And basically, you cannot build. And then there are a lot of different observations, which funnily now I cannot even name. but basically they around 100 years ago, they forced us to review a lot of assumptions that we had. For example, we had to accept that particles or matter in general can behave like a light, or that light under certain condition can behave like matter.
What's the point of having the assumption and then having the reason to change an assumption? Why wouldn't you just go, all right, that's how far we can say for sure, we know. Everything else, it might be that, might be this, but yeah, who cares about it? If you wouldn't be able to actually experiment in the way that you know for sure, why bother?
Well, you bother because you want to understand how the world works, how nature works, sorry.
So
would this understanding of the laws of nature gave us what we have, everything that we have now. All the computers are based on transistors, and the physics of transistors are related to diodes basically, and diodes work through quantum mechanics.
But in a way, wouldn't it be actually the point I made? Because an electrician wouldn't need really to know how electricity works. They just need to know how to harness it, right?
Well,
how to actually use it for an end purpose.
We would not. I mean, we couldn't have been able to build the devices that we have if we didn't understand. I mean, you cannot just try and see what happens.
No, I mean, Bill Gates doesn't need to be an astrophysicist or any kind of physicist to actually build a computer.
Yeah, but
right? So who was the guy who needed to be a physicist to actually build the computer or allow others to build the computer?
I mean, usually when you make basic research, you understand the laws of nature, and then after this, somebody else try to find the practical application of what you understand.
So for instance,
when people discovered quantum physics, I'm sure nobody could imagine that this would be the basis for building a computer or a mobile phone.
Now it's 2018. For instance, I'm not sure. Let's say Thomas Edison was somewhere around the 19th century, end of the 19th century probably. So, and probably the first light bulb at the same time, right? At somewhere around the end 19th century. So at that time, did Thomas Edison, for instance, really think about physics in the sense that,
well, I think
I need to see what they theorized about? Or did he just, all right, if I do this,
Edison was not a physicist, was one of those that made the practical application.
All right, but he knew the theoretical? So he made the practical, but he already knew the theoretical?
Of course.
And the theoretical said that the theoretical laid out how you generate electricity? Or something around that?
I have no idea. But usually, when you make basic research is blind. You don't make research because you are thinking about an application.
Well, you have an assumption, right?
Yeah, but it's blind.
Or an aim.
It's blind in the sense that it's not that you say, I want to build this, so tell me what are the physical laws in order to build this in the best way.
All right.
It's never like this. It's the opposite. You investigate nature, you try to understand how nature works, then you come out with laws, and then afterwards somebody else will say, okay, which is not a physicist in general, will say, okay, usually there are engineers, they say, okay, what can we do with these laws? What can we build? What device can be built based upon these laws? And usually there is a shift. There can be many years to tens of years. Lasers were discovered, I think, in the 50s, but they started to become in our daily life in the 80s, probably, with the application, the counter, the supermarket,
right?
Or the CDs. The application of lasers started many tens of years after, and lasers were first theorized. I don't know when, but again, lasers are based on quantum physics. And it's not that you could come up with build. I mean, it's like trying to build if we didn't know the laws of quantum physics, nobody would come up and think, okay, let's build a laser just by trial and error. You know?
Do you mean that nobody would even try to think to concentrate some light?
No. I mean, the way to concentrate it actually comes from quantum physics. Because
So how let's
laser
say,
works.
So how long has specifically quantum physics and astrophysics been around? Because I would have imagined that astrophysics is
Quantum
something
physics,
in the
it's
20th
100
century.
of years.
So I would imagine 20th century.
Well, first discoveries were in the first decades of of the 20th century. Yeah, 900 or something.
Mm-hmm.
Yeah, the first discoveries.
So before that, nobody could have ever imagined anything.
Nobody knew the behavior of nature at that level. Yes, for example, let me think.
It's just difficult to compare it to anything else,
Mhm.
right? When it comes to innovations, then, because other than that, it seems to me that always people have something imagined that they could actually test, but maybe they didn't have the right tools for that. I mean, the Wright brothers were the first who made the airplanes, right?
Mm-hmm.
Yeah, but before that, people actually tried to figure out how to actually make some devices fly, right? So they had it easier because they could just observe and test at the same time.
Mm-hmm.
Whereas it seems to me that in astrophysics, quantum physics, you either can observe or you sometimes can test something, like physically test as an experiment. Because if you would like to test some astrophysics
Mm-hmm.
theories, it's not possible because we are here in gravity, right? So you need to just observe.
Mm-hmm.
Whereas quantum physics, yeah, you might try to observe and as well something test, but not all, something, right? Yeah, you can make some models that can be tested.
Of course.
So
Yeah,
it seems to me it's so scattered.
I don't understand.
Well, I mean, you have so little tools available. Well,
I mean, if you think that all the technology that we have now is based, really, all the technology we have now, also that clock, is based on quantum physics. If we didn't understand quantum physics, we wouldn't have all that we have now. From this computer, the microphone, the clock, it's all based on quantum physics.
You mean quantum physics as there was a theory and somebody put it into practice, or
Yeah, it's all based by the from calculation and extension of quantum physics in different levels. But yeah, also like I said.
So did they talk about? Let's say, did really? If you say, all right, somewhere around 20th century, maybe 19th century. So did they actually start with, all right, this is quantum physics. This might be useful, but let's just...
No. I mean...
And then afterwards, those types as Edison, Tesla, whatever, came around and said, oh, I can actually use this theory to put into practice. Yeah. Did they really think that?
I mean, there is, of course.
Really?
I mean...
Because they weren't academics, right? They weren't really into studying theories, right?
I don't know. You mean Edison and Tesla? Well,
yeah,
that's the previous century.
I would imagine.
I don't know honestly how it worked, the academic world and engineering world back then.
Especially in those days where you didn't have any communication.
But I mean, in general, there is one thing is the basic research.
Yeah.
The other thing is the applied research. One thing is physics. Other thing is engineering.
Oh, so they were engineers? In a sense like that?
Generally, who makes a practical application of something is an engineer, which is makes a practical application based on the laws that are discovered in general by physicists.
So how come there, or maybe there are, some physicists who are also engineers?
Yeah, of course. Or by physicists that work more in the application of something. I mean, for example, those that built the atomic bomb, again, it's another thing related to quantum physics.
Mm-hmm.
They were physicists, yes. Probably it was a team of physicists and engineers. Yeah. I mean, for example, in order to build an atomic bomb, you had to know how the physics of nuclei works.
Mm-hmm.
You had to know exactly, what is the amount of a certain substance, the amount of energy that you need in order to activate it.
Yeah.
So basically to make...
But did they have any failures? In a sense that, all
Well,
right,
there
we
were-
think this should work, and then they test it. Oh no, something's off, and then they
Yeah,
go
but
back
this
again.
would come more from the...
Because then you have at least a feedback.
This would come more from the engineering side. Like, but, you know, from a form...
so the
you
theory
know,
is always the same, but
yeah,
it's
I
just
mean,
the
a formula
application.
tells you exactly what... I mean, if you tell me how this is called when you have... If you tell me I have a scale,
Right.
you know, where the arms are like this,
Yeah.
and the thing where the balance is here,
All right.
you know, and here I have something that is 10 kilos,
All right.
and this side of the arm is 30 centimeters. What is the mass that I should put here in order to balance these 10 kilos? It's a precise number that you know, and this comes from the theory. It's a precise number. It's not a random number.
But most people would just go, all right, no, not enough, not enough, not enough. Oh yeah, not
Yeah,
enough.
but this
right?
way you don't
Right?
go very far. While the theory tells you exactly, if you know how this arm is long, and how this other arm is long, and you know what weight you put here, you know what is the weight here. It's precise, it's a number. So for example, in the case of the atomic bomb, first of all, nobody would come out with the idea that if you have a very heavy element, this element can be split in two and give a lot of energy. And how do you activate this element? By bombing it with neutron. It's not that you come out with this idea out of nothing. So physicists understood how the nuclei worked, and they also understood that by splitting heavy elements in two, you release energy. And you also know that in order to split a heavy nuclei in two, you can, for example, bomb it with fast neutrons, and these fast neutrons will make the nuclei very unstable, and then make it separate in two and have energy out of it.
So those guys were quantum physicists.
Yeah.
So and you said that quantum physics has some conflict with astrophysics, or the theories,
Quantum physics
or something.
Doesn't match with general relativity. There is not.
So if you say, well, because it sounds you sold me the field of quantum physics right now, because you actually showed, look, just because of the quantum physics theories, you have all this, right? So it means it works. Their assumptions work.
Yeah.
So I would imagine, if I have to guess, and if you say that
the general relativity is wrong.
Yeah.
Well, but also general relativity.
Something's off.
Also
Something
general
off there.
relativity. Also general relativity. For 100 years, we had confirmation of it.
Observations. They can actually make. All right, we have an assumption. All right.
Okay. Look,
theory. We do it. Oh yeah, it works. It really works. Yeah, we're right. So we do it again.
Yeah,
we do it again,
yeah,
and
exactly.
you have nuclear.
I mean, that's how physics works.
Yeah, but astrophysics doesn't have the privilege of actually testing it.
Of course.
And
of course it has.
Applying
Of course it has.
But
I mean, I'm telling you, when you see the rings that come from the from the gravitational lensing, the shape of the ring is exactly the one that you expect, for example.
Yeah, what I mean is that, all right, you have an observation, good for you. Now,
for example, in astrophysics, the amount of neutrinos that we get from the sun is exactly the amount of neutrinos that you expect from the theory. Or, for example, the amount of energy that you get from the sun is exactly the amount of energy that you expect from the theory.
But is there a chance that there's another explanation for all of that would be different from the general relativity? Could it be that there's an alternative theory that explains the same things, and plus,
of course, and
anybody goes along with quantum physics?
Well, that's what we are trying to find in the last 100 years.
So wouldn't it be much more appropriate that the quantum physicists just go over to astrophysics? Because they would go with their assumptions.
But that's
right.
Yeah.
Because now they say, hey, you with the general relativity, you have something.
Yeah,
wrong,
but this is actually more. It's not even astrophysics. When you talk about this level, you talk about theoretical physicists. theoretical physics.
Yeah.
And so here the two fields are intermatching, of course. So there is, of course,
So there's no real dispute, or is there?
there is dispute, but
Let's say, for instance, in the humanities, it's
but
always
I wouldn't,
easy.
I wouldn't
right?
even say that astrophysics is related to general relativity. General relativity is more about is fundamental physics. It's not astrophysics. So people that are studying this are theoretical physicists that deal with fundamental physics, while astrophysics studies different stuff.
But still related to objects in space, right?
Yeah, of course. So, for example,
That's why the physics part, right?
Yeah, for example, in my case, I study what is called high energy astrophysics. Yeah, which is not related with the thing that we spoke about until now. Still, there is quantum physics in it, but
if it wouldn't be related, how come there would be anything? Well, how did you say that they have some conflict, or something's not matching?
General relativity, and there is not.
Because what I wanted to know, are there any, let's say, quantum physicists? I don't know any famous quantum physicist. I guess it was Richard Feynman.
Of course, yes.
All right, so I don't know.
Well, he was more a theoretical physicist, but yes.
Did he or somebody else who were famous in the quantum physics world make fun of astrophysics? But they believe this and
no. But again, this is not. When you talk about general relativity, it's not astrophysics. That's fundamental physics.
All right. So quantum physics doesn't go very well with general relativity.
Well, we don't have a quantum physics description of general relativity, and so for this we know that there is something that we're missing. For sure, there is a general theory with which you can explain general relativity and quantum physics with only one theory. But for now, we have a theory either for one or for the other. And because for sure nature doesn't have a discontinuity, means that we are missing a part. We are missing something. We know this.
All right. So if when you know that something's missing, what do you do about it? You basically, at least, do you know where to look?
Well,
where to start?
There are people studying this for decades, and again, it's one of the most interesting field now, research of people that do theoretical physics. Yeah.
Oh, so that's the role of theoretical physics.
Yeah.
To find the gap.
Well, a lot of theoretical physicists are studying, for example, black holes, because black holes are objects that can be studied both with general relativity and quantum physics.
All right.
And so by understanding how black holes work can give us people think that studying black holes can be one of the things that will make us understand this missing part that we have.
So do I understand correctly that a black hole is sort of an object somewhere in space?
Mm-hmm.
Like, let's say...
I don't know. Well, everything can be a black hole.
Yeah,
I mean,
what I mean is it something that, for instance, if we just try to imagine, if we could travel fast and throughout space, we could actually go near it.
So you want
physically near it.
Yeah.
We could physically go near it. And could it possibly change the assumptions about it?
Well, first of all, people are not even sure whether black holes exist. I mean, it's not that 100% of the community agrees that black hole exists. No.
So there's a phenomena, but different explanations for the phenomena?
Well, there are not necessarily different explanations.
It's just that nobody really can agree totally for calling it a black hole.
Yeah, I mean, people...
Right. So why do they...
It can be just... For example, I mean, there are a few things. For example, another thing that the community is not sure about is dark matter, which is completely another thing.
Yeah.
Same with black holes. Black holes are a consequence of general relativity, and also there is some observation that can be explained by saying that we are observing black holes. And also some more recent observation made 2 years ago that I'm trying to tell you for 2 hours. You still didn't allow me to say it,
So,
which is about the observation of gravitational waves.
all right.
People say that they come from black holes, but still,
And do they base that statement on anything?
well, they base the statement by the fact that now we are talking about something called gravitational waves, which was the last prediction of general relativity.
That there are so what was the prediction?
One of the one of the many predictions of general relativity was the fact that not only space-time can be curved by the presence of a massive object, but space-time can create how they are called
Obstacles?
can create waves of perturbation. So if a massive object is perturbed, let's say moves very quickly or is quickly accelerated,
All right.
the space-time not only curves,
All right.
but can produce waves of gravitation.
All right.
Okay.
But why gravitation? Why not just push-pull forces?
Okay. Imagine that you have the bowling ball, the example before,
Yeah.
in the towel, and then at some point you kick or you punch whatever
Yeah. All right.
the bowling ball. The bowling ball will start moving, and this moving of the bowling ball will create waves in the sheet, right, in the towel.
Yeah.
Okay. The same thing more or less happens in gravity. So a massive object curves the space-time, and when a massive object is accelerated or is perturbed in general, it creates waves in the space-time.
Which creates gravitational waves.
And they're called gravitational waves.
But
And
does that mean the gravitational waves
waves-
force some object to get pulled because of gravity, or doesn't?
The effect of
Are they
gravitational wave is that space is stretched and compressed.
Oh, all right. So
Basically, and this was another and the last prediction of Einstein of the theory. And it took us 100 years to observe them. And then 2 years ago, we observed gravitational waves for the first time.
And how do you observe those?
With something called, well, now we have 3 devices in the world. Basically, there are something called interferometer.
All right.
Interferometer are very simply lasers, perpendicular lasers.
All right.
Okay, so let's say we have one source that produces a laser.
Mm-hmm.
Then the laser is split in two, and it goes in perpendicular directions
All right.
through a length that is very well defined
Okay.
and precisely measured. So the two lasers, the sun source produces a laser. The source is split, the laser is split in two. It
All
goes
right.
like this,
All right.
then they go back.
By a mirror or something?
Yeah, by mirror. They go like this, then
Right.
there's a mirror that reflected. They go back again.
Okay.
Then here they meet, and then they meet and they rematch. No,
So it's precisely
so
the angles.
first they are split, and then they are
Okay.
reconnected.
All right.
And because it was the same laser,
Yeah.
and because the distance was the same,
All right.
then when they meet, they are again with the same phases. They arrive at the final point together. So they basically they sum up,
Yeah.
and they make a precise figure on a screen, which is actually the laser itself. This is what you would see simply if the laser was pointed in a direction.
Okay.
So
So
so this is an interferometer is like this. You have two perpendicular arms. A laser is splitted, and then it's split and
put back again. All right.
Yeah, and back again, and then you have the figure of the laser on a screen, basically.
Yeah. Yeah. So
Okay.
so that whole thing didn't really affect the.
At all,
And-
exactly.
and
I mean, it's
result.
like the old thing was not there at all.
Okay. So.
Yeah. But if something is, for example, one of the two arms becomes a little bit longer, for example, then the distance covered by one of the two lasers will be different now.
Alright.
Will not be the same
Alright.
anymore. And so at the end, when they meet back, they will not have the same phase anymore. There will be a counter phase effect.
Yep.
And so the final figure that you see anymore is not anymore the laser anymore, but as practically speaking, you see
some difference,
higher or lower intensity.
Whatever. Yeah.
And this is what we see. So we have a.
Oh, wait a second. So you expect all that to be the same, but it isn't.
So let's say 330 days in a month.
Yeah.
You see that exactly one dot on the screen.
All right.
Then a gravitational wave arrives, and you start seeing that spot doing this, so becoming more or less bright.
Wait a second. Then gravitational waves can be predicted, in the sense that they
can be measured. This is a detector of gravitational waves.
Oh, wait a second. So basically, it's just you turn it on, and it's all 100% the same image.
Yes.
And then at one point you notice something's off.
Yeah.
And then again it's all back on point. And then because of the something's off, you say, oh, at that point there were gravitational waves.
Well, basically speaking, yes.
But you didn't beforehand. You didn't say, look, now we will put this laser on. It's all 100%. In, I don't know, 40 hours, you'll see a difference. You cannot do that, right? You just wait. Oh, it's different. Now you, that was because of the wave.
Yeah.
Man, that's weird. It means that you just set it up and you don't know when it'll happen.
Yeah, of course.
So
You don't know when it happens. Yeah.
Because I would imagine, look, if you have everything's in place and then at one point something's off, I would imagine, oh, something moved or something like that.
Well, of course, you take care of everything.
Yeah.
No, the device is so sensitive that if there is a car passing 14 kilometers from there, it affects the device. So all the effects, all possible earthquake, people walking in the room 20 kilometers from it, or even the tides and everything is taken into account. You take into account all the effects. That's why it took us 100 years. It's super high technology. And now it's such as...
They probably filmed it, right? Should be on YouTube or something like
probably,
that.
Yeah. Yeah. So the thing is that usually you don't see anything. So
yeah, it's all
it's isolated such as you don't see anything.
So the general relativity didn't predict when it happens, but sometimes it happens, right?
It happens when something in the sky produces them. You don't know what's in the sky.
Yeah, but it would be cool if you would say, "Oh, look, we know that there's a massive object up there. I don't know how many kilometers, but we can calculate the distance. If that thing moves, this laser will go hand."
Yeah. So now I'll tell you. The good thing about gravitational waves in general is that each phenomenon have a very peculiar outcome. So, for example, usually what you observe in gravitational waves are very massive objects that have very high accelerations. So usually what you expected to see were massive objects orbiting around each other. Why orbiting around each other? Because you have a lot of acceleration in this thing. And then, basically the last moment of the orbiting around each other until they coalesce.
Right.
Coalesce, how to say? I don't know.
Do you mean collide?
Yeah, but it's coalescence.
All right. Yeah. They unite?
They unite.
Okay.
So basically, the general relativity predicts a different signal depending on whether you're observing the fusion of two black holes or the fusion of two neutron stars. And of course, given a black hole or given a neutron star, depending also on the mass, on the initial distance, or for example, fusion of black holes gives a signal. You expect a different signal from the fusion of black holes, then from fusion of neutron stars, then from fusion of a black hole and a neutron star, or from an explosion of a star. Each of them have a very, very peculiar signature that again is given by the formulas of general relativity.
Okay.
So general relativity tells you, okay, if you have two objects, two black holes orbiting around each other with this mass, this is exactly this number is the, let's say, frequency of the gravitational wave that you should have.
Okay.
And this number is the amplitude of gravitational wave that you should have.
Right.
And this is how the amplitude and the frequency of the gravitational wave should change with the time. Okay. So they are precise number. The good thing about having a formula is that it gives you a precise number and you can test it. You cannot say it's big or it's small. Big or small doesn't mean anything.
Yeah.
I can say that you weigh more than me, but it's not a number, no? So you cannot falsify it precisely without a number. And 2.5 years ago, for the first time, we had for the first time a signal on a detector of gravitational waves, and the signal was exactly what you expected from the theory. So the intensity of the wave and the frequency of the wave and how the intensity and the frequency were changing with the time were exactly those expected by the theory. So there are theoretical curves and observational curves overlapped, and they basically overlapped perfectly. They match perfectly. So the calculations were exact for the gravitational, but the gravitational waves were measured because the laser got off, right? Yeah.
All right. So does general relativity provide you with the ability to calculate the source of the waves, or the distance of the source of the waves, or something like that, or the direction of the waves?
General relativity, no. The direction, no, for sure. I mean, the device can tell you the direction.
All right.
The more device you have, the more you can make something called triangulation, and the more you can be precise with the position.
Okay.
General relativity can tell you the mass of the object and the nature of the objects. So like I said, black hole or neutron star, because you have.
But then again, black hole is not really all 100% for all.
But this
right?
was just another confirmation of the existence of black holes. Yeah.
Really?
Yeah.
So what do the black hole naysayers then say?
What?
The naysayers of the black hole. The naysayers, the ones who deny the existence of black holes.
Now
what do they
I was reading the other
then?
day. There is a paper that claims that the same kind of observation could have happened with another kind of object that was never observed. So it's a theory.
Oh, so it's a possibility which would explain away the black hole thing.
No, it just that some people said we could have the same kind of observation with the gravitational wave detectors.
All right.
Not if those two objects were not black holes, but if they were another kind of object that until now was never observed. This other kind of object, I forgot what it was. An object that until now was only.
But it's not possible to say that the paper is definitely wrong, or is it?
Well, let's say for now it's a claim of somebody saying that those observations could be. I mean, it's a claim, but there is no confirmation. So for now, it's just a theory. There is no observation.
At one point, general relativity is also only a theory, and then afterwards they made the observations.
Well,
right?
it's a theory, yeah, that had hundreds of confirmation, and made tens of predictions.
And so this paper could be almost the same in the sense that 10 years from now.
If this paper will say, if I'm right.
Yeah.
This assumption of mine implies this other thing that could not be explained in the framework of black holes. Yes, then.
But they didn't do that.
No, I mean I don't know if they had. I don't know what they proposed. But for sure, now you have to accumulate statistics. You have to accumulate observation, basically. Until now, we observed only.
So it's a matter of time.
It's a matter of time.
And technology.
And technology. Until now, we are able to observe only 6 gravitational waves in 2 years.
And there's no chance that those 6 occurrences were caused by 6 different things.
Well, I mean, like I said, all the errors are taken into account
As much as possible.
as much as possible. But an error gives you a noise,
Yeah.
some random noise.
Right.
But the chances of getting a precise wave with a very precise pattern from a random phenomenon are much lower than getting exactly the kind of signal that you expect from general relativity.
And so, in a sense of quantum physics then, would they be able to tell, all right, maybe those gravitational waves actually do something else that you didn't really observe or watch for? As in the sense that if they observe those particle and wave things, are they actually able to kind of transfer into these kinds of observations and tell you an explanation or another theory or possibility to add to that? Or not?
No, this. But I would say that, okay, so basically, after 100 years, we made the first observation on gravitational waves.
Okay.
Until now, our detectors are such as the expected rate of gravitational waves is 1 per month. And actually, until now, in 2 years, the detector were switched on for 6 months because they go under continuous, revision and calibration and stuff. So we actually saw 1 event per month, as was expected. Now they will be switched off for 1 year. They will be switched on around probably the end of this year.
Switched on?
The detector will be switched on around the end of this year.
Okay. For how long?
I don't know for how long, but now they are going through an upgrade. And when they will be switched on,
if they make an upgrade, does that change the previous data or the evaluation of the previous data?
No, they get more sensitive.
Okay.
It will not discard the previous one. It will just allow them to be more sensitive.
Okay.
And after the upgrade, the expected rate of detection will be 1 per week. A few per week.
Oh, wait a second. So that means that the intensity of the gravitational waves is so different that actually they occur a lot more. It's just that they could.
Yeah, of course. I mean, also now I'm talking to you and I'm moving my hands.
Yeah.
I'm producing gravitational waves, but they're not detectors that are able to capture them.
But this movement, wouldn't I would imagine quantum physics would say, all right, by this movement, I just move the air and all the particles in it.
But there's something different
to that direction.
But you're also changing the geometry of space-time by doing this, and because of this, you're producing gravitational waves.
Do the quantum physicists use space-time as well for their calculations or whatever models?
No, you don't.
So when does space-time become,
or maybe yes, but I don't know,
become relevant for any sort of let's say models, observations, and stuff like that? Quantum physicists would say, well, I don't really need it.
I don't know this. I don't know.
Because you know what the most interesting thing to me seems that it should be in a way that physics is just physics, right? But then again, you have those total subdivisions, and then it seems that the quantum physics wouldn't be really into astrophysics, but you at least have theoretical physicists for that.
No. Well, first of all, in astrophysics there is a lot of quantum physics. A lot of quantum physics.
But
I mean,
but
how the
but not vice versa, or is there?
Well, not vice versa, because a lot of things, for example, of quantum physics were understood through astrophysics observation. Yes.
Oh, and still some things are not really.
No. Again, the mismatch is not between astrophysics and
general relativity.
It's general relativity, which is more that's fundamental physics.
Also, quantum physics has a problem with general with basic physics.
No.
Fundamental physics.
I mean, it's more that we don't have a theory that describes both at the same time.
Oh, it's in fundamental physics is not a theory, right? Or is it?
Fundamental physics studies, I would say, the general force of nature. Yeah, or fundamental physics, or we call it just theoretical physics.
Oh, so fundamental would be theoretical.
Yeah.
Oh. And but you don't have practical physics. You have different fields of applied physics, and
you have usually you have theoretical you have.
How many types of physics nowadays could you find?
Okay,
first it quantum physics, astrophysics.
Okay, first of all, you have the big separation is between observational physics and
applied
and theoretical physics. Usually, who makes observation?
Well, you said theoretical physics.
Mm-hmm.
And the other?
Observation.
Oh, observational.
Yeah, or experimental.
All right.
Those that let's say those that makes.
But experimental would be something different, wouldn't it?
Well,
because you model something.
Experimental physics is observational physics is the same as experimental physics. The only difference is that in astrophysics you cannot call it experimental astrophysics because, like you said, experimental. In astrophysics you make observation, but because the experiments are made by nature already, so you don't have to set them up. But basically, what you divide are those that take the measure and analyze the data, and those that take the data and then make a theory out of the data. So these are the two separations, basically, from theoretical physicists and experimental physicists.
But when did that divide happen?
Well, because you need a specialization in everything you do. You cannot ask somebody,
But then it gets sort of weird.
You cannot ask a lawyer to drive an airplane. It's normal.
But a lawyer would be able to learn how to fly an airplane.
The same. It's just that at some point, during your career, you say, okay, I will be a theoretical physicist or an experimental, just depending on your attitude. And then you either work on one side or the other.
So that would be, in a sense, that if a quantum physicist would like to go into astrophysics, he wouldn't be able.
No, sorry. Now we're talking about there are experimental quantum physicists and theoretical quantum physicists.
Okay.
There are experimental astrophysicists and theoretical astrophysicists. So one big division in any field is the theoretical and experimental.
All right.
Let's say. So each field has the two of them, at least.
All right.
And then among the fields in physics, I would say there is fundamental physics, which is that study the laws of nature.
Yeah.
Then there is astrophysics. There is cosmology. There is physics of the state of matter. There is electronics.
Chemistry used to be a part of physics, right?
But now it's considered like something different. What else?
But is it justified to be different?
Well,
I mean, if you have quantum physics and astrophysics, why not having just chemical physics or something like that?
Well, there is such a thing. There is chemical physics, yes.
Oh, all right. But it's not. It's something a little bit different than just general chemistry.
Well, they study different stuff. Now I don't know what, but they study this different stuff.
Because the
thing is that, like in medicine, you have many different branches, but not because they all fight with each other, just because in order to be good at doing something, you need to specialize yourself. You cannot know deeply everything. A genius could.
Yeah, sure. I mean, they need, but nobody really told them to do more and more and more. It just so happens that they can do it. I mean, you can. I mean, medicine would be quite diversified field every time you look at it. So, and sometimes in history you can see probably one healer for everything, and in modern times you can find 3 different types for one and the same need, right? But there's no real fixed need for them to be 3 or 1 or 2. It's just that, all right, what does the market
Well, I mean, of course,
established.
of course, nature behaves only in one way.
Yeah, that's what I mean.
I mean,
it's subjective when it comes to those things.
I mean, the reason why we have many different branches is just because, in order to study and to be expert in something, you basically you separate it in branches, but that's it.
So Einstein was the one who established general relativity, or he just
He's the one. No, it's his theory.
So he created the theory. Does that also mean that he created another field of physics?
No, I would say general relativity is fundamental physics.
So he was a
theoretical physicist, studying, well, not only general relativity. He also studied. He was one of those that made the basic observation of quantum mechanics. He was a theoretical physicist that had interest in many fields, in astrophysics, in
quantum physics.
In quantum physics.
All right.
And in fundamental physics. Yeah.
So basically all of them.
Yeah. Well, he was Einstein.
And who's now the Einstein?
Not now. I would say there is not such an Einstein. Now that you know,
because everybody
now everything is
satisfied with general relativity, or
well, no, because genius like that maybe they happen once every century. For sure, in the future there will be somebody else at his level that will build a new revolution, but for now there is no revolution. Now,
well, what was another German Max Planck was a physicist at that time?
Yeah, exactly. Yeah, so he was one of those that made the fundamental discoveries on quantum physics. Physics. Yes.
Oh, so he was basically quantum physics.
Then. Yeah. Well, quantum physics was, I don't know when the word was invented, but
at that time
before that time it didn't exist. There were people that were investigating nature on small scales.
All right. And
understanding the laws of nature on small scales. Planck is the guy that made what is called the Planck constant. That basically is the fact that the observation that something in small case, when you observe the small or the world of something that very small, nature of that level very often doesn't behave gradually, let's say,
right.
But for example, energy can be released only in quanta. So that's where the word quantum comes from.
Quanta would be a specific portion?
Yeah, specific portion, yes. So for example, one of those...
Wow, but they didn't like to use the word portion.
Yeah, it could be called also portion physics. Yeah, could be called.
All right.
Quantum. So basically, for example, one of the observation is that, for example, let's say that you have an electron around the field of a proton, no? And you give energy to the electron, no? It would
be difficult to imagine what does that imply, giving something energy.
Light, for example. Light.
You mean just shining some light on it?
Yeah.
And how does that mean that he gets energy?
So, imagine to have the moon is orbiting around Earth.
Right.
Let's say, if you imagine to give the moon a little bit of energy.
You mean just shining a lamp on it?
Anyway, to push it, whatever. Imaginary experiment. The orbit of the moon will be affected. For example, the moon will go a little bit farther from Earth.
All right.
Not due to the fact that it has more energy. The next stable orbit will be a little bit farther.
All right.
And let's say if you give a very small amount of energy, the change in the orbit will be very small. If you give a big amount of energy, the change in orbit will be big, but basically it will be continuous. So
you mean
but
a literal push?
But
right? You don't mean shining a light on it?
In every way. You can also...
Wait a second, you mean that if I shine a light on it, it will change its trajectory?
Sorry, it's not what I meant, but in principle, yes, you can change... Because light behaves as a particle,
All right.
light has a momentum, and you can accelerate a piece of paper through light. Yes. If you have a laser and a piece of paper, through the laser you can make the paper move.
Ah.
Yeah.
And they literally do that. So it would mean that if I have a small toy car and just point a laser?
In principle, yes. Yeah.
Oh, it's not...
I mean, yes, you can. I mean,
I cannot make it a literal car move.
I don't think you
but
can
it
make
should be that way.
Yeah, but I mean, you can do it. Actually, there are people thinking about making...
Because that would be great if you could actually move something by just pointing.
I mean, in principle, you can do it. I mean, in the same way in which, in principle, I can make you move because you are attracted by my hands. You don't see the effect because it's very small. So in the daily life, you don't see it, but it's a phenomenon that can be measured and that exists. Yes.
But
and people
up till now, nobody has moved a car with a laser.
Not a car, but I don't know the experiment. This is called the radiation pressure, and yes, you can. I'm sure there are experiments where you measure it. It's something that we know. It's not. Some people came out with this idea, and it was not observed. It's observed. Yes.
All right.
And for example, people.
I still need to wait for.
Yeah.
It just moves, right?
In principle, you can
I
do
don't
it.
touch it, but it just moves because of the
like I said, you
laser.
cannot see the mouse moving just because I put my hand here.
Yeah.
This doesn't mean that gravity is not true. Just means that the effect is too small, and that the friction between the mouse and the table is bigger than the effect of the traction as a consequence of my hand.
All right.
Doesn't mean that the theory is wrong. It just means that there is something else that is stronger. In this case, is the friction between the table and the mouse.
Mm-hmm.
In the example that I made is that the friction probably between the car that you're talking about and the molecules of air is bigger than the effect of the acceleration from the light, but the effect is there.
Ah, but would it be possible to get the friction so little that the laser actually moves it?
Of course.
Really?
Of course. I'm telling you, people are thinking to build a probe, a space probe that could arrive to Alpha Centauri or anyway that could explore the space through radiation pressure. So basically, to have a laser and basically to make a small probe accelerate through a laser from Earth.
Ah.
And this would give acceleration that are much higher than anything we built until now.
You mean a faster acceleration than a missile?
Yeah, absolutely. You can actually arrive in Alpha Centauri in a few years. No. What the fuck am I saying? In 40 years. I think.
Yeah, but wait a second. Then it should. So then they should build some, I don't know, trains with that or something like that, right? On Earth, transportation. Then it should be used for transportation.
It wouldn't be effective. I mean, it wouldn't be effective, of course. Like I
said, because the other forces on Earth.
Sorry. Is it true that if you blow on this screen, your breathing will apply a force on the screen?
All right.
So why don't you move the screen with your blowing on it?
Because it's not that strong.
Yeah, exactly. So that's why you don't build trains with this mechanism. It doesn't mean that the mechanism doesn't exist. It doesn't mean that your blowing potentially doesn't have an effect on the screen. It just means that the effect is not relevant in this context. That's why you will never build an engine where inside there are cats blowing on something, just because it would be ineffective. But doesn't mean that the effect is not real.
But the probe with the laser?
Yeah, this
it would be faster than a missile.
Yeah.
So it means that
because you are in empty space and the probe is very small. In empty space, you don't have friction with anything.
Yeah.
And can be accelerated. Yes.
But it wouldn't be literally faster than a missile. A missile would be faster then, right?
No.
Because a missile would be apply more force, right?
the total acceleration will be higher than, I'm telling you, it can reach Alpha Centauri in 40 years, potential, or 70 years, I don't remember.
Yeah, that's somehow difficult to understand, I guess. Because as far as I understand, it's like this. Now I'm on Earth. If I blow on the screen, it won't move. But if it would be outer space without friction, it will move fast.
Of course.
All right. But if I put a missile on it, it will be much faster. Because because a missile would be like thousands or millions of blows. That's what I mean.
Okay. Let me think. Well, the difference is that in this way, basically you will, I mean, if the I don't know, honestly. I think it depends on the amount of, the amount of energy that you need to accelerate a missile or such a thing. Most likely the amount of energy that you need, a missile that will have that kind of acceleration, the amount of fuel that you need to accelerate a missile up to Alpha Centauri would be enormous. And you cannot possibly build a missile like that because the amount of fuel will be larger than a missile itself, no?
Probably.
While most likely...
So it's the most efficient way with that thing.
Most efficient. The device...
Yeah, I get that.
Yeah.
Yeah, cool. All right. You have been really patient with all the questions. That's cool. No, because it's interesting. It's not that you could every day meet an astrophysicist.
Yeah.
But you said that you quit your job, right?
I quit my job. But actually,
because you didn't like to argue with people about quantum physics and astrophysics.
But I would like to finish about gravitational waves first.
Sure.
So the observation of gravitational waves was one of the biggest discovery of probably of the century, or at least of the last tens of years.
I think the iPhone was.
Also. And the cool thing is that it will give us an enormous tool to understand a lot of things that now are still question marks in physics in general and astrophysics also in particular.
Are those question marks mostly questions about why does that particular thing happen, or would that thing actually happen? What type of questions do they ask?
I would say both. So, for example, let's say, because
all the predictions of Einstein of the general relativity have been observed.
Yes.
There's no
but
more
for
left,
example,
no more left. Right?
For reasons that it will be difficult for me to explain. Observing black holes are very extreme objects where the effects of quantum physics become relevant even in a massive object. Don't ask me why, because I cannot explain you this.
But is it a theory that they become relevant?
Yes.
Or
the effect of quantum physics become relevant in black holes.
But not otherwise. Or somewhere else.
Not somewhere else. And also gravity is put under very strong test, because we never tested gravity under something that is called strong field.
All right.
So black holes are objects where gravity is really tested in a way that were never tested until now. Okay. They're very extreme. You
mean with the laser? Or with something else?
Laser is a detector.
Oh,
the laser is a detector.
So it wasn't a test, or was it?
Sorry, the thing with perpendicular laser, that's a detector. Just like a telescope is a detector of light. The interferometer is a detector of gravitational waves.
So what did you mean with tested?
when you make a theory, then you make tests of the theory. You make observation that can be either that can prove wrong or prove correct a theory.
Yep.
Gravitation was never tested in circumstances like black holes.
All right.
Basically because until now, we never made the kind of observation, we never observed two black holes merging like we did apparently 2 years ago for 5 times until now. And because, like I said, until now we only have 5 cases of observation of black holes, which is poor statistics. But like I said, when the devices will be switched on again, they will be much more sensitive. We'll be able to observe few events per week.
All right.
In 2025, we're gonna have a new upgrades, and the expected rate is gonna be 1 event per day. So you understand that we will pass from 0 observation in the history of mankind to 6 observation in 2 years to 1 observation per day.
All right. So if you have already observations and then you say, all right, I'll make it more sensitive, so I'll have more observations. All right, we get it. You can make observations.
Well,
so
because
what?
because
so what?
so what? Because
Yeah,
the more observation,
already some
the more observation you have, the more statistics you have, the more you can see how nature.
The same thing. You can see more of the same thing.
No. Because in one of those same things, there can be some hidden effect that you didn't see until then. Of course.
Just because you have more of them?
You have more statistics, so you have more cases, for example. You have more phenomena that can happen.
So you have more cases of detecting, let's say, the gravity waves, right?
So we will have more detections. Let's say we will be able to observe one gravitational wave per day, right? Then, for example, if let's say there is a very subtle behavior that now with 5 cases we cannot catch, just because now everything seems fine. I mean, it's like
you just detect.
I mean, it's like anything. It's
just detect.
It's like I ask you. I don't know.
So I guess you know.
I mean, it's like I ask you what is the what is the perimeter of this house? If I ask you to make the experiment 1 time, you will come up with a number. If I ask you to do it 10 times, you will have 10 different measurements of the same thing. When you do it 100 times, you can tell me, look, most likely this is the precise number, and this is the error that I make when I make the measurement.
All right. So you'll just make, let's say, you will get more numbers after the comma for certain metrics. Then.
Actually, this example that I did was not even good because it's the same thing, which is the perimeter of the house that doesn't change. But the more you observe, the more observation you have about the same phenomena, the more you can see how that certain thing behave under different conditions, and if maybe there is something unexpected, no? So when you observe, let's say, after 365 days, or with 10 years of observation, you observe maybe 1,000 of black holes. You can agree with me that
in different locations, right?
You can agree with me that the thing that you can deduce by observing 1,000 of things are different than those that you can deduce from observing something 1 time or 2.
But wasn't it the exact point about the falsification of scientific theories, that you could go around and say, look, I see 1 white swan, I see 2 white swans. Oh, like there's
I see what?
The swan, the black swan theory, or the black swan principle, I guess it's called.
I don't know it.
Well, the principle that you are not able to prove anything about that all the swans are white.
Yeah.
Right? Because you could go around and say, oh, I count 1 white swan, I count 2 white swans, I count 3, I count 100, 1,000. But actually you say all swans are white unless you'll see another color. And then you say a black one. Oh, right, yeah.
But this requires new observations.
So it's not the amount of observations. You just want to see something different then.
Well, the more you have observations, the more it can happen that either something unexpected happens,
All right. Yeah.
or just it happens. Or just that it helps you to see more precisely a phenomenon and maybe discover patterns, for example, that you didn't. If you observe something only 5 times, you cannot come up with a pattern. Maybe if you observe it 1,000 times, you will see that there is a pattern that is not predicted in the framework of the theory, and then the theory can be proven wrong, for example.
Oh, so
or simply you will observe something that is just a signal that is not predicted, and that's where the discovery will be, and that implies that there is something.
But the problem would be the detector. The detector is tuned specifically for those things it measures, right? So it wouldn't be able to find anything else other than what it's designed for. It would be, for instance, for the gravitational waves. And then if you can make it more sensitive, okay, it's more sensitive, but still it's just looking for those particular waves, right? Or for those particular occurrences. If something else happens, then would that detector get that?
Of course.
Then I didn't understand the detector then. Because I would imagine it's just tuned specifically for a certain occurrence, and when that occurrence happens, certain results appear.
Okay.
And then you can just make them again and again and again, and once it's more sensitive, more and more and more.
No,
but still it will just prove the same over and over and over again.
No, I mean, I mean, it's like, how do we know? I don't know.
But honestly, you sold me quantum physics.
I mean,
I'm totally in quantum physics now.
I mean, a telescope is a detector of light, right? Then doesn't mean doesn't mean that there is no point of observing the sky, because then everything that you need to know is already there. I mean,
if you have the detector, or if you have the telescope only at one point, only directed at one point, then at a certain time you will be able to sell. Look, I think I have had enough, because there's nothing new there.
It's not true. Absolutely.
Well,
it's not true, because the night sky.
Yeah, because people are looking like this.
No, it's not true. Absolutely not.
Well,
absolutely not.
Well, do you mean
because if you look at some object, the behavior of the object changes every time. Of course, depending on the kind of object you're observing. If you observe,
but you don't expect it to change. You just rule you just basically say that there's a chance that something will change, right? But you don't expect it to change.
You make observation. And through the observation, you understand how the nature works. This doesn't mean that.
Yeah, but you make priorities.
This doesn't mean why do you build a telescope at all? Once you have one telescope and you observe the sky one night, that's it. What's the point of building a telescope or making observation every night of the year? That's what you are saying.
Because there's a chance something new will occur.
Of course.
All right.
I mean, everything that we know it through observation. That's why we make observation of the sky, for example. I mean, that's the point of studying anything. And I mean, I don't understand why you say, so why you make a new observation?
No. I'm not saying why you would actually look. If you will want to just point the telescope at one point in the sky, you can do that. But since you are human and your time is running out, you would probably be more interested in having some recording device. Just looking into it, and now you can go off and do something else.
Of course.
Right? So afterwards, you can say, oh, my recording device tells me same. The same. Yeah, nothing new. All right, I get that. Yeah, for sure. But then again, you also make those type of detections also limited because you have priorities, right? So what are those priorities? I mean, if you say to me, well, our priority is now to make the detection device more sensitive, so it can detect more often.
Mm-hmm.
All right, with the expectation that something new will happen, nobody really knows, right? It's just a possibility that something new might happen. If not, we'll go
gravitational waves
something
are
well.
a completely new window at the universe, and the amount of things that we can understand through gravitational waves are enormous and probably even impossible to imagine. I don't know how to be more clear about
But those
this.
GPS satellites, for instance, are those the results of quantum mechanics or astrophysics or quantum physics or astrophysics or both?
General relativity.
So quantum physics, no point.
I mean, the technology, of course, there is quantum physics in how you build anything.
Also, quantum physics allows you to prove general relativity?
No.
Oh.
The effect that I was telling you before is an effect of general relativity.
All right.
Then how you build a satellite, of course, you need electronics.
Yeah.
And of course, you need transistor and computers. And of course, you need quantum. It's a technology based on quantum physics.
Mm-hmm.
But the effect comes from general relativity.
All right.
I mean, it's like I tell you, how do you observe the sky? Through a telescope that has a lens. And so a person that builds a lens or a mirror is something that has something to do with general relativity. No, what does it mean? And the technology to build the device has nothing to do with what the device is used for.
So would you say that the only reason why quantum physics has certain aspects that are not compatible with general relativity is just because there's no filler theory or filler observation that could actually unite it?
Yeah, I mean, what I wanted to say before...
And maybe those detection devices could help to do that?
What I wanted to say, yes. When we will have those observations, we can study in detail and with great statistics the behavior, for example, of black holes. And black holes are super powerful. Those kind of observation will allows people that study fundamental physics to understand things that can be understood only by studying black holes. Yes, that they will provide us with observation that we never had until now. Will provide us with kind of observation that we didn't have until now. So it for example, gravity will be tested in a range of energy, for example, where we never tested it, for example.
All right.
Quantum physics will be tested in a range of energy where we never tested it until now. So unexpected and new effects can happen, for example.
But it's out of the realm of a sort of established theory that predicts that once you, for instance, there is no astrophysics theory that says, for instance, if you will make the detection device so sensitive up to this point, you should observe that and in such and such a manner. Or is there? Because you said the general relativity was so peculiar that it actually made predictions that afterwards actually were observed.
But of course, they can, for example,
because I would imagine
general relativity, the idea of general relativity, I mean, it's data. The more you have data, the more you can...
Yeah, but come on. You probably should be able to differentiate that sometimes you have useful data and sometimes unuseful data. Data is just data, whether or not it can be applied.
Everything that we know about the universe comes from data.
Yeah, for sure. I mean, from useful...
Everything is data. And
but you should be able to differentiate between unuseful data.
Unuseful data... I don't know what you define unuseful data, but...
Well, it depends on the context, but I would imagine that you should have some point to say, oh, this is data, but it's totally useless.
Well...
Useless data.
But useless, something can look useless, but maybe it's not if you look at it more deeply. It depends. I don't know.
That's already philosophical,
For example, the typical... For example, I was saying, general relativity came out, one of the reasons why it came out because there was a small deviation on the orbit, I think, of Mercury that was not coherent with the theory of gravitation by Newton. So let's say the theory was predicted a certain movement, a certain orbit, but then observation showed that there was a little discrepancy between the expected value, the expected position, and the real one. These discrepancies cannot be explained in the framework of Newton theory.
Okay.
They can be explained through general relativity. That's why actually one of the reasons why Einstein came out, because he wanted to interpret those data. And if you didn't have data as boring as the position of Mercury with respect to the sun, that somebody else could say, oh, but this is boring because we know exactly where Mercury is there. If you didn't have years and years and years of orbits and position of Mercury, you would never notice that there was a discrepancy that was not expected by the theory, and theory of relativity would not be here now probably. And somebody else could say that was a boring data because you know exactly where Mercury is.
No, I'm not saying boring or not boring, but I say sometimes you should probably be able to say, oh, it's useless. That data is useless. From all we know, from all the theories we know, from all the predictions we have made, this will be useless.
Probably, but what's the point with this? I don't understand.
Well, in the sense that you can make those priorities according to what gives you the most or gives the biggest potential of useful data. And if you have useful data...
But why you had to prioritize? Well, for example, gravitational detector, they get gravitation away from everywhere in space.
Actually, do you mean to say that, for instance, if Einstein, let's say, wouldn't have even bothered of explaining the discrepancy, would that mean that there's no chance that GPS satellites would be in orbit?
Well, if Einstein wouldn't come out,
if
nobody would come out with coming out, if until now nobody would come out with a theory.
If Einstein wouldn't have existed,
and if somebody else wouldn't have come with the same theory on his behalf, we probably would have tried to make GPS, but then we would have seen that they were wrong, that they didn't give us the right position. So maybe at that moment somebody else would come with trying to explain it. But GPS would. So
it would be almost inevitable.
Yeah, I think
to make.
Well, I'm not deterministic in general, but yes, probably if Einstein didn't come out with this, probably somebody else would have at some point or another.
So are you able to say now that the general relativity is true and
until now was always proved true, but
it needs some addition just to make it compliant with quantum physics?
Yeah. This is, like I said, one of the most active fields in general where theoretical physicists are working.
Because I would imagine at that point when you can say, all right, quantum general relativity seems to be true. Quantum physics needs some guidance just to make this whole thing work together. So something's missing. Now you are still making basically priorities. All right. So what's the main focus point now? What will be the first questions to ask? And then wouldn't it be actually all up to your imagination almost? Because nobody can give you any answer, right, at that point, because there's no answers. There's no observations even for the missing link or for whatever, right? Does it mean that you have to just well, maybe it could be like this. Yeah, just maybe afterwards we can test that one or try to observe that one.
Like I said,
does that point become imaginative?
New observations in general. I mean, it's like you're living in a room and you only have one window facing that side of Riga.
And I think there should be more. I think there should be more.
Yeah, and you try to describe the world outside of this room through that window.
Yeah, and I see. Hey, I would need to go outside.
Then all of a sudden you open a new window, and this new window allows you to get more conclusion. Okay,
Yeah, but
gravitational waves are this new window.
But the impulse to go to the next window was beforehand. The next window didn't actually make my impulse. My impulse made me go to the next window, or seek the next window, or seek the next angle to look from. The impulse came before I actually made the observation.
Of course.
I wasn't satisfied with the
impulse,
already existing.
The impulse is the
My
lack
imagination.
is lack of satisfaction and the will to know more. That's why we are building more devices to make observation, because we know that we discover more with more observation. That's why physics is built on observation, because physics is built on observation. The more observation you have, the more you can discover. Now we have a new window that we just opened it, and the amount of things that we can understand and discover are endless.
Wait a second, you told me that gravitational waves were 2 or 3 years ago?
Gravitational wave were first discovered...
Well, 4 years ago, 2014?
In September of 3 years ago now. So it was September 2015.
Ah.
Yeah.
All right.
And like I said, this is the beginning of a new technology. So like everything, like it will grow for sure. Like when we started to observe the sky in gamma rays, the first gamma ray telescopes could see 3 sources in a year. Now the current gamma ray telescopes see thousands of sources in 1 year. So the same will happen with this technology. The technology will get better, we'll have better observation, more precise, and so on.
Is there a subdivision even in between astrophysics?
Absolutely, yeah.
So at one point,
Actually,
is there a general map?
You see,
right.
I still didn't tell you what I do. I don't do any of the things that we said until now. I work in the field that is called high energy astrophysics.
Right.
In particular, I'm an observer and observe the sky in the field, in the range of energy of gamma rays.
All right.
So basically, I'm a gamma ray astrophysicist.
Okay.
And gamma rays are one energy band. Other energy bands can be X-rays. Also in the X-ray there are the soft and the high X-rays. Another energy band is optical, another is infrared, ultraviolet, microwave, and radio, more or less. All these are.
Does it just all depend on some frequency or something like that?
It depends on your device. You cannot make a device that can observe all the frequencies at the same time because the technology is completely different.
Yeah.
Gamma rays telescopes are built with semiconductors basically, and they are pair production telescopes. So basically a gamma ray telescope works actually with quantum mechanics again. There is a photon, a particle arriving on the material. The photon creates a couple of electrons and anti-electrons. The couple of electrons and anti-electrons, the trajectory of the electrons and anti-electrons are tracked inside a semiconductor, and then through the semiconductor, you can reconstruct the energy and the trajectory of the electron and anti-electron. And from this trajectory, you can understand the energy and the direction of the initial photon. So as you see, it's extremely complicated and it's based on quantum physics.
Well, the trajectory, you mean the power that it came?
The direction. I mean, let's say...
But also the speed at which it came?
Not the speed, but the energy. The energy of the photon.
So it is the power then, right?
The energy.
So the fastness or...
The energy... Well, the fastness, no, because the
energy, isn't it dependent on the speed?
No, because the speed of light is constant.
All right.
In the case of a wave, the energy depends on the frequency of the wave.
So the energy would be what? Similar to power?
Power is a measure of power. Power is energy divided by time.
Oh.
Yeah. Anyway, you can measure the energy of the photon by measuring the energy of the particles that are created by a photon. Because basically a photon disappears and it creates particles.
All right.
Again, for another quantum physics phenomenon. it creates a couple of electrons and anti-electron, positron is called. And the electron and anti-electron have exactly the same energy of the original photon they come from. And by measuring the energy that is released by these particles inside something that is called calorimeter, from this energy you can measure the energy of the particles, and for the energy of the particle you measure the energy of the photon.
Mhm.
While from the trajectory of the particles inside the semiconductor, you get the trajectory of the direction of the photon.
But the photons are coming all the time, right?
Yeah, I don't remember. Depending on the energy, you have different rates, but yeah, they're coming all the time.
So the conclusions are, what type of conclusions can you make from those observations?
So in let's say every different energy in astrophysics shows you a different aspect of the same phenomenon.
All
Let's
right.
say.
All right.
In the same way, if you had infrared glasses here, and you would put infrared glasses, you would still see this room, but the information that you would get from the infrared glasses, it would be completely different. Because with your naked eyes, basically you see the light from the lamps and the reflection of the light of the lamps on the walls and all the different objects. And these reflections have different energies, and they appear to your eyes, and they are, let's say, digitalized by your eyes as colors, basically.
All right.
As colors. So basically, your eyes give you a measurement, basically, of the your eyes make you see the colors, and the colors are related to the energy or the light emitted by the different objects that are here.
All right.
If you put infrared glasses,
I'm still seeing with my eyes, just through something,
but
something that blocks something out, right?
the infrared glasses are actually sensitive because there is something called black body radiation. Black body radiation is each body produces a certain radiation depending on how hot it is.
All right.
No? And if you change the temperature of the body, also the color of that body will change.
All right.
Okay. When you put infrared glasses, the infrared glasses will show you the temperature of the object here in the room. So you would see, for example, usually like in the movies, people, in the militaries, actually, they have infrared glasses or whatever, because they allow you to see a body is for sure hotter than a wall. A wall maybe is at 20 degrees, my body is at 37. So this allow you to see a person in the night, not because the body of the person is reflecting the light or something, but just because the body itself is hot, and because it's hot, it emits light at a certain frequency, and that frequency falls in the range of infrared.
Okay.
If I was a little bit hotter, you could see me with your eyes, but not because you could see me with your eyes also in the dark. Not because I'm reflecting the light of something else, but just because I'm producing light myself, because I'm hot. So for example, infrared glasses give you completely different information about this room. If you put infrared glasses, you see hotter and colder part. So the same, if you had ultraviolet glasses, they're not, or X-ray glasses or radio glasses, they will give you different information about this room. So the same happens with the universe. You can observe the universe with different glasses, and each of these glasses or telescopes give you different information. So for example, the infrared sky looks different from the optical sky, that looks different from the X-ray sky, They look different from the gamma ray sky, and they look different from the microwave sky.
All right. So what you're saying is that essentially, somewhere, all of the time, somebody is watching the sky with, let's say, an infrared.
Yeah.
But there's no real aim to it other than let's just observe and see what happens, right?
Let's start.
Maybe at some point the clouds will get warm.
No,
or something like that.
I mean, let's study the sky in the infrared, because infrared gives you some amount of information. And in general, nowadays astrophysics is built with a collection of data from all the possible telescopes. It's called, now most of the things are done with something called multi-wavelength astrophysics. For example, I'm a gamma ray astrophysicist, but when I used to write papers, I used to collect data also from X-ray telescopes or from optical telescopes,
All right.
and put all the information together to have a complete picture of a certain phenomena.
All right.
For example, you can study
A phenomenon or observable object?
phenomenal observable object. I mean, for example, you can study, I don't know, a nebula or a pulsar or even a star at different wavelengths, and if each wavelength gives you different information, and then you put together the information and you understand better the same object. Yeah.
But there's no real expectations in that particular instance that, something will happen, something should happen. It's just that, we will look at it with different
usually
angles.
Usually you make either survey. I mean, you either, depending on the telescope, depending on the policy of the telescope, depending on the plans of the team, you can either choose to be in a survey mode and maybe to observe all the sky for a short time, or you can choose to observe a particular object for a longer period. It depends on your goal in the specific moment. Or different observers can buy and allocate a certain time, because let's say I study that particular object, so I will, let's say, make a request and get 5 hours of observation of a certain object just because it's an object that I want to study better. No? And then I can combine it with the same observation, with the observation of the same object made in another period of time, or maybe simultaneous observation being made by other telescopes, combine the data and see what comes out, for example, what you can deduce. For example, one of the biggest discovery that me and my team, and in general of high energy astrophysics, was something called gamma ray flares from the Crab Nebula. Crab Nebula is an object that we know actually for many hundred of years, and it was one of those boring sources that was behaving always in the same way. And we thought that we knew everything about it, but then in September of 2011, me and my team, we discovered that in a particular day in gamma rays, that object was like 20 times brighter than any other time that was ever observed. So that object was always super stable, always stable. That day we observed it with an emission that was 20 times brighter. It was completely unexpected. And then we made, usually in this case, you send an alert to all the other teams in the world that observe the sky either in the same range of energy, but especially in all the other range of energy. And you do what is called multi-wavelength observation. So after we made the announcement, all the other telescopes in the world, well, not all, but all those that could, they turned their telescope toward that position, and they made observation of that phenomenon to see what was going on. For example, in the X-rays, because we have made this observation in the gamma rays. To see what was going on in the X-rays, in the optical, in all the other frequencies. And to the surprise of everybody, nothing was going on. So the only changes, for example, were in the gamma rays. And also this information, this simple information, that is more quantitative is qualitative before being quantitative, already gives you information. So it gives you that for whatever reason, it's a phenomenon that is restricted to the highest energies, and whatever is happening on that star is not happening in lowest energies. It only emits light in the highest energies. So what are the implications? Why this happens? What kind of phenomena can produce increased emission by a 20-time fold only in the gamma rays? All these are questions that come from the observation.
Mm.
And then there was another gamma ray telescope that made our same observation, and then we observed this behavior other 7 or 8 times throughout 7-8 years. And now people are trying to understand why, what, all the implication.
So before that, did you know that gamma rays act single
Before that,
with the individualistic, that in a sense that if you observe gamma rays, then it doesn't mean that anything else would be affected as well.
No, it's not like this precisely.
You knew that they can act individually, right? They can be detected individually.
No, I mean, it's not the gamma rays are...
It's
not really like this.
The changes in gamma rays can be individually, and nothing else might be affected, right?
Well, let's say this object called the Crab Nebula is an object that is visible at any wavelength, from radio to gamma rays.
All right.
And
any physical object can be observed in any of those, right?
No.
How come?
For example, the sun is almost invisible in gamma rays because the sun doesn't emit in gamma rays. It doesn't have enough energy to produce gamma rays.
Oh, okay.
Or many pulsars are visible only in radio, for example, a little bit in optical, but not. But there are gaps in a lot of other energies. No? So the Crab Nebula, for example, emits at every wavelength, and you could expect, for example, that if there is an increase in the energy in the gamma rays, there would be also an increase in the energy. If there is an increase in the intensity in the gamma ray energy, you could expect an increase of intensity also in X-rays.
Okay.
It could happen depending on the phenomenon that is producing that increase, for example.
Yeah, but you are not really sure what produces it, right?
You're not sure, but this observation, for example, can rule out some phenomena and cannot rule out some other phenomena. So that's it. So before that, it's not that we didn't know that gamma rays could be there. It's more that we didn't know So before that, we didn't know. The Crab Nebula is the most typical, let's say, is the representative object of a class that is called pulsar wind nebulae. So pulsar wind nebulae is a kind of object. It's a compact. It's a neutron star.
It's a classification of an object.
It's a classification. It's a neutron star with a nebula of electrons and positrons around it that produce lights for different reasons. Radiation for different reasons. And until that time, we didn't know that pulsar wind nebulae could have a variable emission, just because all the pulsar wind nebulae observed until then were always stable.
Okay.
And B, because the theory that was built out of the observation in order to model pulsar wind nebulae was actually self-coherent. So the theory actually
didn't predict it. So
or what we knew from the pulsar wind nebulae didn't predict it.
Yeah.
Of course, because everything that we knew came from observation. Observation never showed.
But could it be the case that at one point or another a theory is too soon made? I mean, what would be what would be the risk if you would make, let's say, an assumption, you make the observations, you do whatever you need, but you don't make a theory, you just do other observations, and that's about it. And at one point, maybe then you would like to see the theory getting put together, but then you already have the observation so much.
What usually happens is that theory and observation go together. So basically, you do an observation, then you build a theory.
But the threshold for, all right, now
you make observation, then you build a theory, then you make new observation, and then you refine the theory.
Or either
then you make new
one.
observation, and then you refine the theory. So the theory is refined with the new observation. And the more observation you have, again, the more precise with the new technology, the more you can have a more refined theory.
It's just that it seems to me that astrophysics might be one of those few areas where to make a theory you should probably wait like 20 years, and before that it might be just too soon to make all sorts of predictions.
But again, there is not something that, I mean, everything will, as like I said, observation and theory go together.
Yeah, I know, I understand what you mean, but in the sense that if you have to put it on paper, and if you have to evaluate it against established assumptions, theories, whatever, it just makes it that much more difficult. Because, all right, now we have new observations, now we have the gamma acting up, nothing else did. All right, what did the theory say? And stuff like that, right?
Exactly.
Yeah, and it's just, if at that point you would be able to say, well, there's no real theory up till now, very good.
Well, no, because, I mean, whatever changed after this observation was not completely trashing in the garbage the old theory. It's just a small extension of the original theory. And actually what we are...
So who's the originator of the theory then?
So what we're understanding now is that all the theory of pulsar with nebulae is correct.
Wow.
The only thing is that there is an additional phenomenon happening from time to time that was not included in the previous theory, and this new phenomenon produced this other observation. So basically...
So now it's up to the next observations to actually determine what occurrence did that.
So basically, let's say the theory, the emission from pulsar with nebulae comes from particles that are accelerated through a phenomenon that is called Fermi acceleration. And the Fermi acceleration, that is the model for the acceleration of the particles, and the emission from the particles through the mechanism that we know, that is synchrotron and inverse Compton, explain perfectly the emission from pulsar with nebulae in general, in what is called the steady state. So the state,
just a regular,
the stable state.
All right, but it doesn't.
Additionally to this, there is an additional phenomenon that is called magnetic reconnection. Magnetic reconnection is an additional way to accelerate particle that is different from the Fermi acceleration. And basically the observation just tell us that together with the Fermi acceleration, that if you want I can explain you later, together with the Fermi acceleration, there must be a second phenomenon of acceleration of particles, because only this phenomenon can explain the observation. So basically what we know now is that together with Fermi acceleration, in this kind of objects, there is also magnetic reconnection acting, basically.
So wait a second, you know already the phenomena or not?
I mean, the observation that we make in the flaring state, so not in the stable state, can be explained in the framework of magnetic reconnection.
Oh, so in a framework?
Yeah.
Oh.
So,
but could it be explained in another framework as well?
as far as we know, nothing else can produce those observations.
Ah. So the explanation for those was already established then, right?
What do you mean? Those observations, let's say, triggered a lot of studies in magnetic connection. There are tens of theoretical papers published after that observation, trying to explain the paper and to get the numbers. And let's say 90% of the paper.
Oh, so when you observed it, it wasn't that you already said, "Oh, it's because of that framework."
No, when we observed it, it was completely unexpected.
All right.
It was a complete. It was a.
I got it.
It was a completely unexpected observation.
All right.
That's why it was a big discovery
Mm-hmm.
in 2011.
All right.
2010, actually. 2010.
Got it. I get it. It's been 3 hours. Edoardo. You want to show
Oh
this?
man, it was 95% this, my god.
It's not bad.
Yeah, not bad.
Not bad.
But I know that it can, when you start to get into the subject, just get endless.
I
Yeah,
like it. I don't mind.
Okay,
You
cool.
want to show the instrument?
Ah, yeah. I almost forgot that I played this instrument.
Yeah. You have a
Mine is
specific
It's,
bag for it.
yeah.
So what's the instrument called?
The instrument is called RAV. R-A-V. And by the way, if you want to have this RAV, I will give you a link and you will pay just the same price, but they will give me 5%.
Oh yeah. We can
Because,
put a we can
because
put
I'm
a
a
link.
I collaborate with them.
We can put a link for sure.
Yeah. So, okay, it's like this.
Let me just.
It has a central note. And then you play it from bottom to top.
How come it makes different notes? It seems so.
Yeah, it makes different notes depending on the side of these little tongues.
Are they different?
You see, this is small, so it vibrates very quickly. It makes a high pitch.
Alright.
This is big.
Oh, so the sizes are different. Oh, interesting.
Yeah,
All right.
and it's basically a percussion with notes.
Hmm.
The amount of notes is limited because it's difficult to build an instrument that has more than 10, 12 notes. But probably there will be evolution in the future, but you can see you cannot increase the number of notes unless you want to increase the size of the instrument, right? So you can only play in a particular key, which is the key of this instrument. This is a sort of A minor. So if you ask me to play in D major,
Oh, you would need to make it relative.
yeah, well,
Proportionate.
yeah, but I mean, if you ask me to play any song, I cannot play any song with this one. I can only play whatever is inside these notes that I have.
But you could actually make it just take the notes down or up as needed and still play proportionately all the notes.
If yes and
Probably.
no. Yeah. I mean, you cannot play in some very limited case you can.
I would
Wait a
imagine.
second. Okay. Yeah, so the limitation from the notes can be partially covered by the fact that it's actually also percussion, so you can play it both melodically and percussively, so you can add more variety also with the percussive part, no? So you can make like a simple arpeggio, like or you can play two notes together. or 3 notes together, 4 notes together.
Was it from the top 40?
From the
Well, what kind of song was it? I mean,
No, this was
Was it your own?
no,
or-
just I was just improvising 100%. I was actually talking and I was showing you the instrument, and then I
Yeah.
just started to randomly play.
So is it always improvisation for you, or are there any?
Not always.
are
I mean, of
any
course.
songs?
I mean, you have songs, of
Yeah.
course, and but also when you play a song, there is always a big component of improvisation.
So how's the instrument called?
This is called Rav, R-A-V.
Just 3 letters.
Yeah,
Rav.
or Rav drum if you want, or Rav bast, but you can just call it.
And
Rav.
from where is it?
It was invented by one guy in Russia. That's why
Really?
I was in Perm 2 weeks ago.
It's sort of interesting that this comes from Russia.
Yeah.
Interesting.
Yeah. So, for example, one composition of mine. Yeah, I mean, I can make one of mine, but
So how fast did you learn this?
well, I started to play a similar instrument to this one, which is called hang,
Also from Russia.
5 years ago. The hang was invented in Switzerland
Oh, interesting.
in 2000. And then 3 years ago, one guy from Russia was trying to reproduce the hang, and
Yeah.
he came out with this idea that is substantially different.
All right.
So the principle is different, because also the way it sounds is different.
It's metal, right?
It's metal, but basically you play hang and rab in the same way. Although they, electric guitar and acoustic guitar,
Well, this is
they are very different.
this is just the
but
only
you,
acoustic,
but you
right?
can play it in the same way.
Yeah.
So this is very different from the hang,
Mm-hmm.
but still you can play it in the same way,
All right.
or 90%, 95% in the same way.
And what got your attention to actually play these?
Well,
kinds of
5 years
instruments?
ago I started to play hang because I saw somebody playing it years before. And
Did you
I
play an instrument before that?
I was playing percussions, like not drum, like djembe or cajon.
No.
Also, this one you can play it if you want, like a djembe. You can do also African rhythm, like. played more percussively or more melodically, depending on what you
Where
want to do.
where is this mostly played? Is it played in, I don't know, some institutions, some events, some gatherings, some cultural
Well,
festivities?
there are of course there is an underground world, so all the lovers on the instrument gather in festivals and stuff.
I somehow think I've seen
Probably
specifically you, but I'm not sure.
me.
I mean,
Maybe because I sent you a video a few days ago.
No. I think I somehow think that another guest of mine mentioned you, but I may be mistaken.
Well, the world is small.
Because you once you played it, I was like, didn't I see it somewhere?
Well,
I don't mean that.
I'm not the only player. There are. Well, now there are a few thousand probably players.
I need to ask Eric. I think
Eric?
if from a Canadian dude. He's a musician, and I think he mentioned something like this.
We know. I cannot say that we know each other. We all know each other, but chances that we know each other.
he's not a player of that.
Chances that we know each other.
But yeah, I think he showed me because he wanted to show me some unusual instrument playing. I think, well, I might be mistaken, but yeah, it's somehow I feel like I've almost like seen it.
Cool.
Like déjà vu.
Yeah, I understand. Yeah, if you want to play it, I saw you are curious.
Well, I mean, I get the point of it, but yeah, I wouldn't be able to actually do
anyway, this idea of
useful
podcast is amazing. I really think I'm gonna do it myself when I get home.
Are you in a podcast?
Yeah,
oh, yeah, for sure.
I really like it. So
I would imagine you have the biggest option of actually get in some people gatherings with tourists. All right, as a street musician.
Well, no, of course, I'm also a street musician.
Yeah,
and a lot of people that play this instrument are street musician for a few reasons. Well, basically because it's very handy. Well, more or less.
Because it seems.
And second, because it's very unusual, so people are very attracted by it.
Because it seems, well, maybe it could be used for concerts, but then again, it seems like a standalone.
Okay, so
right. It seems like a standalone.
Okay, so usually you play it either alone. There are also people playing it in bands. I also mix it with electronic. Actually, today I told you I was working on a composition with electronics. Alone also is okay, especially if you add some effects, some reverb, some echo. It sounds really amazingly. Until now, for example, I use it in meditation events, yoga events, relaxation events.
I just wanted to tell, at one point where you played multiple notes together, it sounded like massage music.
Look,
just those relaxing Himalaya CDs. Do you have a CD? Can you also make a disharmonious tone? Can you create disharmony as well? No. So you can't go wrong with this.
Yeah, you cannot go wrong. Almost. Yeah, so that's why it can be played by complete beginners, and the result that you will have from the beginning will be nice. You know, if you just.
So what is your aim?
My what?
Is your aim to have
aim
multiple records out with this type of music? Because this is a niche type of music,
niche,
very popular.
So how I'm earning money with this?
Yeah.
In different ways. Until now, I was busking. I was making street art.
Mm-hmm.
And playing in some. I played in weddings. I played in weddings. I played in some dancing events, some festival. Yeah. Let me think.
Well, those are performances essentially.
Okay. So until now, I was either busking or playing in events. I played for also for meditation events, relaxation events in India, in Russia also. Performances.
Yeah.
Then recently I came out with my format, and I talk about science like we did today with the music. Actually, we could have done exactly what we did today.
Yeah.
Let's say we've been talking for 3 hours.
All right, let's start over.
Yeah.
Now.
We've been talking for 3 hours.
Yeah.
Let's say that every 15 minutes we stopped.
All right.
It would have been my format, more or less. In my format, I talk 15 minutes.
But the flow.
Well.
What about the flow?
Well, I actually prepare at home, so it's such as after 15 minutes you get to a conclusion or whatever I'm talking about.
All right.
So it doesn't get necessarily too technical. It's
All
actually popularization, but it's more about. I try to stay in this dimension, of dreaming, of feeling. So I talk about.
Well, you have to be light.
Yeah, I talk about the sky. I show images from the universe. So my event is like this: 15 minutes I talk with slides sometimes, and 8 minutes. I play showing images like from Hubble Space Telescope.
All right.
Then again, 15 minutes I talk and 8 minutes I play for 1 hour. And I started to make these events recently. I made 2 in Italy and 2 in Russia. And for example, in Russia, I earned quite good, around I earned 150 to 100 euros per event, which is not bad.
And how did you promote?
The place where I made the event were already like famous places, so they had their own followers.
Wait a minute, you were a performer in a series of performers?
Sorry, I made 2 events in 2 different places.
All right.
They were like, I don't know, one was a place where people make concerts in general.
All right.
Another was more a place for conferences.
All right. But it was only for you, right? That particular event was only for you. It wasn't a summer festival.
No. It was only for me, and like first time 40 people came, second time 50 people came.
Yeah.
And the promotion was made by the play itself, by the place that organized the event.
So they sold tickets.
Yeah.
Oh.
Yeah.
And what was the promotion then? Because
they have their own Facebook page, I think, and followers.
Because they probably then used some buzzwords, right? Some buzzwords. Like,
what does it mean?
Well, some attractive words, attractive phrases, or whatever. Oh, well, meditation, people, something like that.
Yeah, probably. Yeah.
So, yeah, because it truly reminds me of the massage music type of relaxation or meditation.
Well, there is people for sure that do also massage. Actually, I have one called Surfing Host in Copenhagen. Well, it's not his profession, but he likes to make massage. and he has a little room with a table. Sometimes he makes massage. And I gave him my CD, like I will do with you. And he said, "Oh, thank you so much. Now whenever I make massage, I listen to the CD, and people like it a lot. Everybody tell me that it's very good for relaxing. For example, he likes it for this."
It's exactly for that type of thing.
Yeah.
That's why I feel so interested in that instrument, because it seems like the almost the perfect type of instrument that you just sit down, put the microphone near, and just start recording a full album.
Yeah, well, I wish I was able, because as well.
I mean, you did 3 songs.
Yeah, I know, but then
and most of them was improvising.
But
right?
Then when you had to record for real, I mean, I have my own CD actually, but it took me forever to make it.
Yeah, but nobody really notices any bridge or chorus or whatever.
Don't tell me this, please, because this is really related what I was telling you before 4 hours ago or plus about discipline. Like you said that you wake up at 4:30 and that you read, you do this and do that. The self-discipline, especially now that I quit my job, it just became a nightmare because I don't have it. Of course, potentially I could record 1 album per day. Potentially, but I don't do it.
That's what scares me.
I don't do it.
Because
potentially
really
I could
possible.
Potentially I could make 2 videos, 3D videos per days, but I still didn't do it. I'm just because I'm not efficient, but that's why I like this discipline.
Yeah, but the music for you with the format you told me, it seems like
that's one. It's quite.
15 minutes.
It's working.
Well, if not 15 minutes, then 20 minutes, and then afterwards, it doesn't really matter. But you could definitely, at least 2 per hour. Yeah, man, you're a beast.
The other thing I'm working on, I am working on a online tutorial. Sorry, not online tutorial. On a tutorial. This is actually my priority in the last month, but I didn't even start. To make a tutorial to sell like through platform like Udemy, because like I was telling you, the instrument is new, so there are a lot of beginners and a lot of people that really they play like this without having any base on what is the rhythm, how to make.
But could you make for instance also some popular music on it? I mean, could you recreate some radio song?
Well,
because that would be something that catches the attention.
There is one guy that made, not with this instrument, but with the hampan or hang.
Yeah.
He, for example, made a very famous cover of Mad World. From whom?
Oh,
Mad World.
Yeah. I remember that one.
And it's big, of course, it sounds amazing. He also sings, and it's working very well.
Well, all right, then I get that it's the niche effect.
It's still a niche, but actually it still didn't come out. It rarely came out from the niche, for some reason. But probably in the future it will happen.
And every esoteric person in the world will love it.
Yeah. Well, every esoteric person in the world knows it already.
No. Maybe they have heard it, but haven't really seen it.
No, seeing it is different. That's why whenever they, oh my god.
Yeah. So it's fairly surprising if you think of it, because it has no additional needs. You just put it in your lap and you go. Very good.
And so on.
Do we end with that?
Yeah, let's end with that.
All right. I'll put the minutes. I'll put the minutes so people can see actually the part already where this is on. Well, I'll check on the timeline.
Ah, okay.
Yeah, so they can see. I think it was around 3 hours when we started, right?
Oh, man.
So yeah. I'll put that info in there, and you'll give me the link, right?
Yeah,
With all
of
the details.
course. Of course, because
Alright.
now recently I became sort of ambassador, collaboration with these people that make the instrument, and through the link you don't pay it anymore. It just they take some from it, like a 5 to 10% to me. So
very appropriate. Very appropriate. All right. Thank you very much.
Yeah. Thank you.
Thanks for everybody else. See ya another
Bye-bye.
time.